Welcome everybody to day 4 of the AGI-23 conference. We are in the Accelerating AGI with Hardware workshop room here. We're starting off the day with our lead presenter, Rachel Sinclair. She's the CEO of Simuli. A doctor in complex systems and working on compression algorithms, hypervectors for pattern matching, and generally hypervectors for AI and the acceleration of AGI. So thank you very much and welcome, Rachel.
Thank you, Amy. Okay, hopefully everyone can hear me okay online, if people are watching online or if not. What I'm going to do is we've kind of have the day structured so that in the afternoon we can do a bit of a discussion, and also so we can go and maybe join some of the other presentations in the other rooms. We're kind of multiplexing, which we'll see later is very important for learning and stuff like that. But so I'm going to give a very quick, probably quickest ever history of hardware. Very quick, because I'm assuming lots of people have kind of been around the space long enough to kind of see what's going on. And then I'm going to jump into what Simuli is working on in terms of hardware and these accelerator chips that we're building. And then we'll hear from our esteemed colleagues, Peter and Adam here, on some related sort of technical notes about what you can do with kind of the core tech stack that Simuli is using called Hyperdimensional Computing. Which we'll explain more, don't worry. And then we will hear from Dr. Ben Gertzel on the NPMC pattern matching chip. So that is kind of our trajectory today. I think maybe after I give this little brief hardware introduction, if anyone wants to grab a coffee or we just take a couple of minutes to collect themselves and really come into being alive this morning, we might do that. So anyways, let's get started. So I'm just going to go ahead and start with the motivation here. So why do you want hardware, specialized hardware for something like AGI or AI in general? Well, first of all, it lets you develop stuff quicker, right? So if it takes you 2 hours to run your program that you're just tinkering around with, and now it only takes you 2 minutes, we can test a lot of stuff faster, right? And so this is what we've seen largely over the GPU deep learning revolution, where as soon as we got GPUs, which accelerated deep learning, we were very quickly able to just test and mash a bunch of stuff out and say, this works, this doesn't work. Now that has good and bad things, right? I mean, one of the bad things is we've kind of lacked a structural kind of learning of how do you construct neural networks in these architectures for this is what works because I tried it on my laptop and it works. But I think overall it's a positive thing, right? Because if you're trying to use a type of math that's not fully optimized for current hardware, you might end up thinking that it's actually performing way worse than it would if you just had optimized hardware, right? So we might be limiting ourselves just in that way. The second motivation for wanting hardware is that I personally, and hopefully other people feel this way too, is that we want AI and AGI. And I'm kind of going to use AGI as a blanket term. I know we don't like to do that, but as a blanket term to include AI for just the purpose of this first talk. Because we don't have AGI, so AGI hardware is just not quite there yet, but we'll get to the emerging section. So we want things to be sustainable, right? We don't want to accelerate global warming too much or climate change, however you want to call it. I don't want to get political, but we want things to be sustainable because we like the planet. And also we want things to be sustainable because it's very expensive to run these current deep learning systems. So just as a ballpark figure, ChatGPT takes about $700,000 a day just to run inference. And that certainly doesn't make things democratized for anyone to just jump in and start training these large language models, which is kind of an issue because you probably have very bright developers and researchers who would love to work on kind of tinkering and adapting these systems. And what you end up with is only these large corporate conglomerations who have the best, most powerful tech. But you guys kind of already know all of this. And then there's this law of parsimony, right? So if you're trying to develop something that is somewhat intelligent and kind of fits in this evolution of species, maybe evolution of technological species, you don't want something that's resource greedy. And we'll kind of motivate this more and more as we go along. But there's this law of parsimony. If you want to know the full details, there's a bunch of this in the AI field. You can kind of dig into it. But the core thing is that in order to kind of specialize into your own modality, whatever your embodiment is, which could be a decentralized, mega Hyperon-based system, or it could be like a centralized Sophia-based system, or any of these things, you need to match your signal inputs with your computational processing power, right? So that's kind of the idea there. And we don't want to have to just buy new server space or increase the amount of hardware we're using just to learn more things. That's kind of the core idea. So I'm going to start with this quote, "Let Zeus be a stone." I'm not going to try to pronounce the guy's name who said this around 2nd century BC. But what we're seeing here is one of the first analog computers. It's glorious and amazing. It's called the Antikythera mechanism. It's one of the oldest known examples of analog computing. So before we had this digital computing, many of you probably know, we had what we call analog computers. And I am just gonna grab my phone so I can keep track of time, guys, because I have no idea how long I've been up here for. Okay, so this is a diagram for what the Antikythera mechanism could be implemented in kind of the way that we view circuits and hardware today, right? So it's kind of complex, which means it's really cool because it comes from 2nd century BC, and it's somewhat complex compared to maybe what we would think computers would be like back then, right? And essentially what this Antikythera mechanism did was predict solar eclipses, right? So the idea behind this analog computing, one way to think of it is that you're taking processes of the natural world and you're creating some other natural processes to model that, right? And we'll talk about a trade-off that happens later. But you get massive information capacity because you're taking natural signals, the natural world, wave functions, particles, things like that, and you're forcing it through some flow. It doesn't have to be mechanical. Normally it's mechanical. It can also be electric. And you're using that to compute. So you're using the natural world to compute on the natural world, right? So there's a couple of really awesome kind of hallmark examples, starting with the differential analyzer, which came in about 1928. This thing could compute differential calculus, right, using integrals. Then we had the Mark I. The Mark I was super fantastic at controlling what we would now call autonomous weapon systems for the military in World War II. So it was hooked up to its giant turret-looking thing. You've probably seen it on, like, if you've ever played the game Battleship or something. But you guys have probably seen it just in general. And then there's something called ammoniac, which is actually a hydrofluidic computer, which uses water and fluid dynamics to model the UK economy. So there's other various analog computers that can also model economy. And then there's one of my favorite analog devices up here, the non-periodic oscillator, which is developed by Leon Chua. He's really cool. If you haven't heard his name, he was a really awesome scientist. And so he developed this thing called the nonlinear circuit, which is essentially like a chaotic attractor state circuit in 1983. And between 1983 and 1988, this nonlinear circuit could be implemented by this thing called a cellular nonlinear network. So the acronym CNN, which is terrible now because it really competes with convolutional neural networks, but they're completely different things, totally different. And then we had buckets of water invented. So they weren't invented then, but there's a paper on reservoir computing about computing in a bucket, right? So that's the paper I'm referencing here. If you haven't read it, it's super interesting. But you can also use something as simple as a bucket of water to compute PDEs, partial differential equations, things like that. So you can use all sorts of mechanical, electrical, natural things in the world to do quite complex computing, is the point. And one of the most recent examples is brain scales, which is an analog neuromorphic circuit, which can model, spiking behavior in the brain. So I've kind of separated these two classic examples of analog computing down here, because if you ask me, the abacus, which is that thing, there's one over there in the room. I should have brought it over here for demonstration. It's the little thing with the sliders, and then you push them over, and you can count with that thing. An abacus is kind of a digital analog hybrid, right? And it's the same with the Jacquard loom. So the Jacquard loom used to be a textile weaving. You take punch cards, basically, these giant wooden punch card slats, and you put it into this giant contraption with all these strings attached, and it would weave a particular fabric pattern. So these things were mechanical in one sense, but they had discrete spaces. So analog computing is over continuous spaces of information, whereas digital computing is over discrete spaces. So a lot of people think maybe analog computing is kind of specialized or primitive, but what we can show, and Leon Chua's cellular nonlinear networks are a really good example for this. So this image processing, 3D surface analysis, biological vision models, all of that could be computed with CNNs, and I mean the cellular nonlinear network versions. So we have this kind of rich environment of analog computing that is somewhat general depending on the core infrastructure. And this hasn't gone away, right? So there's been this evolution of analog computing over time. So now we're going to switch gears and we're going to talk about digital computing. So this is one of my favorite quotes ever by Richard Feynman about what is a digital computer, right? So if you just take the idea that it is a filing system, glorified, high class, very fast, but stupid filing system, that's what we can maybe say about digital computers. Because essentially what you're doing is you're learning a set of instructions which shuffle data around. And if you can tell the computer what those instructions mean, it is essentially like any file could do, or, at least back in 1986. So I know I'm going very fast, guys, but I want to get to the fun stuff. So we have these digital computers, and for the sake of this, we're talking about electronic digital computers, right? There's like I said, the abacus, the Jacquard loom, which are questionable if they're analog or digital, depending on who you ask. But this all started with earlier Charles Babbage, but we can kind of sum it up to John von Neumann and Alan Turing. And about, I think, 1956, he had this ADC paper, which describes kind of the fundamental architecture that almost all digital computers have used now. And this paradigm means that you are going to store the instructions, the programming, and the data together. And what you're going to do is you are going to move the data around to the logic to compute. So in, if I can remember my dates, but there's this thing called the ETAN 80170NX, super cool name. But that thing was around 1983, I think, and that was one of the other first examples of AI accelerators. So we've moved away from general purpose computing for the sake of electronic digital computers, and now we're just talking about AI accelerators, right? And just as a tidbit for anyone who maybe isn't quite caught up with the history of AI, Alan Turing's Can Machines Think computer came out in 1956, I think. So this kind of idea of computers that can compute like humans, this kind of AI, AGI idea has been around before these accelerators. So Snapdragon brings this up to 2015, right? So Snapdragon was using AI on their mobile phones. So you can think of their architecture here, this 820 architecture, as a form of an AI accelerator. And then we have this thing called FPGA. This is field programmable gate array. So field programmable gate arrays, FPGAs, they're really fantastic because you can kind of, they're a bit modular, so you can move the logic around. So you can move how things are going to be computed around. And there were several in between, you know, the von Neumann E10 and Snapdragon. There were several versions of FPGAs that were attempting to accelerate AI, or what AI was at the time. And then around 2016, we got the modern GPU. So if you know the history of NVIDIA, the GPU came much sooner than 2016. But what we think of now is at least the 1080 architecture, which is kind of what broke into the deep learning scene, is our modern GPUs. And if it's not just NVIDIA, there's AMD, there's other people doing GPUs. And NVIDIA wasn't the first. But anyways, this is kind of the very vague and loose history. I wasn't going to go through every single AI accelerator, but we've gotten caught up to this important word here, ASICs, or application-specific integrated circuits. And ASICs are kind of all the rage now. And I should make a clarifying note. GPUs are ASICs, but they're more general purpose, these graphics processing units. So these ASICs, what we have now, is basically dedicated devices to offload all of the AI compute to a particular chip that's integrated with the motherboard, usually a PCIe connection, right? So there's tons of them out there. We don't nearly have enough time to go through every single one. But what I did want to do is kind of go through kind of the most recent things that we've seen. So we can talk about Cerebras, Salmonovas, GraphCore, and then Meta just came up with their MTIA chip. So what we're seeing here in these yellow boxes is some just general hardware specs about them. I'm going to let you read this stuff. Not all of them are filled in because these companies have very different ways of telling you what their technology does. They all don't tell you the bandwidth. They all don't tell you how much on-chip memory they have, and they all don't tell you how many floating point operations they have. They're a little bit obscure in their data sheets. But the Cerebras chip is interesting so these are all regular AI deep learning accelerators. We can think of them as, right? The Cerebras chip is interesting because it's very large. It's huge. The chip is like literally, it's massive. It's like this big. And so it's very good at putting entire models onto and then computing with an entire model. So entire GPT-4 models. Cerebras just released on Hugging Face, if you're familiar with that software interface. There are Cerebras GPT versions, which you can run on their novel hardware, their WSE2 chip. Then we have this company called Salmonova. So they sell entire data bank servers, entire data servers, just like GraphCore. Both of these guys, they sell the full work block. And Salmonova's kind of catch here in the AI space, they've created this sort of data flow pipelining, which does some sort of funky pre-processing. And their main catch is bandwidth. So they focus not on size and getting entire models in, but instead on bandwidth and how to move data through the chip as fastly as possible. And then we come to GraphCore, which is quite an interesting company which Simulize is currently kind of exploring their IPU architecture, which is Intelligent Processing Unit. And this IPU also comes in these data pods. And GraphCore uses a graph compilation method that's static. So if you're familiar with TensorFlow versus PyTorch, PyTorch is a dynamic graph compilation, whereas I think I may have just said that backwards. PyTorch is dynamic, TensorFlow is static. So this has both pros and cons, but the idea is that they have some 3D lattice, which they have kind of near memory processing fabric, which means data can be routed through the logic pretty efficiently, but it's set up in a 3D graph-like structure, so to speak. So anyone who's doing any sort of graph neural networks or graph type of learning, you might want to check this out. They have some examples on their free cloud compute. Anyways, I'm not here to pitch for them. So, so Meta, we all know Meta, right? So they just announced this inference AI chip, this MTIA. And essentially, there's not too much details on the MTIA chip right now, but essentially what they've done is they've optimized this for their recommendation systems software that Meta has developed internally. And What's interesting is all of these very new chips are all using 7 nanometer processing technology. So this is size of the transistor, okay? And there's this idea, called Moore's Law. I'm not gonna harp on it too much because I can really get caught up on the whole conversation. But essentially, the question is, whether, I don't want to get into semantics, but there's a question of like, how much smaller can we keep making transistors, right? And there's some work that's done, and I'd be happy to point anyone to the wonderful references on this work. When you get down to the size of a single atom, say a phosphorus atom, which is about 1.95 nanometers or an angstrom, you start to get these really weird physical interactions between particles, and we can't really make transistors smaller than that without calling it quantum computing. So we do have single atom transistors. They were invented in 2004. Invented is probably a strong word. They were probably idealized much earlier. But in 2004, we've had these things. People have been working on them, trying to get them to work outside of what we consider normal quantum computing. But the idea is that if we're at 7 nanometers now, and really we're able to process 2 nanometers today, right? So these chips came out a couple years ago. So today's technology is at 2 nanometers, which we'll start seeing in 2024. So next year we'll start seeing these things on the market. And we can get as small as 0.195 nanometers. And Moore's Law says, there's a doubling every year of how much smaller these things get, or having, rather, which has been slowing down to like 1.5. So if you just do some back of the envelope calculations, we had about 9 years until transistors have gotten to the realm of quantum size, which will be very fun and exciting. But anyways, so we're looking at emerging technologies, right? Because we want to increase our compute performance, but we're kind of approaching this thing where the transistors are as small as they're going to be before we start calling it quantum. And again, another Richard Feynman quote. If you can't tell, I really like this scientist. But the idea is that we don't want to just throw more compute at everything, right? We need to find a way to get more increased performance out of computers without just miniaturizing everything or just adding more. So we're going to talk a little bit about kind of some of the emerging technologies that are coming on the scene. So we have this superconductors, which is largely what we're going to talk about, has to do with processing and memory, photonics, and there's other cool stuff that we could maybe slash, including photonics like DNA computing, other funky stuff. And then of course, just good old quantum, which I'm not going to discuss, but hopefully in the future, it's in superposition whether or not we'll talk about some quantum stuff. Okay. So I'm just going to cover basically the in-memory computing, which has to do with superconducting. And I think it was 2014 or 2011 that Intel came up with this alternative paradigm to the John von Neumann architecture. And the idea is that you basically, you take your logic to your memory, right? So you're no longer taking your CPU and calling up data from the hard drive and then routing it through RAM and shuffling data all around to compute. You just compute wherever the data lives. So this is a rich history of processing and memory. So earlier we talked about Leon Chua, right, and the Chua circuit, which has first, second, and third order degrees of nonlinearity. And this kind of was the original theoretical foundation for what processing and memory, which is part of this in-memory computing business. This is kind of how it all started with Leon Chua. And there's some other people that were involved in that, of course. But basically, what you can do is you can take these in-memory or processing and memory circuits, or these memristor circuits, nonlinear circuits that Chua made, and you can pair them with non-volatile memory, which means the memory doesn't go away. It stays there when you turn the computer off and on. And what you end up with is a greater density of logic and compute than typical hard drives with the same access time as DRAM, right? So this sounds like really powerful computing, right? And typically, the way that we do this, the core hardware technology that this is done with, is what we call magnetic tunnel junctions, or MTJs. And the alternative paradigm, besides creating a magnetic field and then kind of shooting a voltage and expecting the voltage to just collapse or kind of assume a state within this magnetic field, is this spin process, but it's less popular. So one of the cooler things that has been around for a while, but it's just now getting to like at volume scale manufacturing production for hardware, is this thing called Joseph junctions. And this uses superconductive materials. So you're probably familiar with semiconductors. The transistors use silicon. This is semiconductors. Now we're getting into superconductors, right? So it's kind of more metal-based. It's really neat stuff. And there's a commercially available example of this processing in memory memristor device called SDC. You can buy it now for researchers, people, you know, and anyone who wants to play around with it, you can go buy this thing. And then there's some other examples that people like to argue about whether or not they're actual memristors, like phase change memory, which Intel has been working on for a while, MRAM, ReRAM, stuff like that. But the key takeaway, I'm kind of running out of time here, but the key takeaway is that we want to bring the compute to the data. So we want to bring the logic to the data. And then the von Neumann architecture, which is the prevailing compute architecture, it's limited because you have to move the data from the hard drive to the RAM via the CPU. This is an oversimplification, but you can kind of think of this as the core bottleneck of why maybe you don't want von Neumann architecture and you want processing and memory architecture paradigms, which don't have a really solid name yet. And the idea is that if you put the logic right next to the memory, then your computations become faster. Everything becomes faster because it takes time and it costs energy to move data around. And so this means that you get increased performance because your density of all your logic and computing is smacked all close together. So the way you route power physically through the chip is a lot more efficient. So you automatically, you know, if you do everything right in the chip architecture, and depending on some other various factors, you can often get increased power performance, right? So lower power usage. And if you use a non-volatile memory, you can get long-term storage, which sounds like it might be good for lifelong learning and AGI or something like that, right? And usually, because we're using things like magnetic tunnel junctions or Joseph junctions, the actual computation of JJs or MTJs versus transistors are faster. So the actual switch, the circuit works faster than typical transistor. So I have some references. But that is the very fastest brief overview of AGI accelerators. And now we're going to switch gears a little bit and go into kind of what Simuli is working on, why we're working on it, and then we'll continue on with our stuff. So I'll just switch tabs. I don't know if anyone wants to grab a quick coffee. I think we're going to hold questions till the very end after lunch.
You don't have to, I think.
We don't have to? No, okay. If anyone has any questions, real quick, I'll drink some of my coffee. You guys can just watch me drink coffee too, that's
So,
fine.
quick question. You mentioned that the 2 nanometers coming out in 2024. Right now, there are 3, right? Nanometers.
Yeah, we have 3
But those
nanometers.
were all at 7. So, why aren't there 3 nanometer recent chips?
Very good question. So I have a couple kind of statistics that can help give an intuition of that. I mean, I can't give you this is the answer, but
Yeah.
first of all, when you create chips, let me just give a brief overview because I think it's helpful anyways. Basically, you simulate the overall design and you iteratively kind of guess, or you don't guess, but you guess and check methods saying, okay, if we put all the circuits this way and we use this processing geometry and this size transistor and we put this logic here, blah, 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 we get this compute performance, power, memory, speed, blah, 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 right? And so that's how people design chips through this iterative simulation process. It's not the best method, but that's what we've been doing for basically ever. And then once you have something called a GDS2 file, this is basically your final blueprint. You send this off to the fabrication factory. These are the people who's going to cut up the actual silicon or, you know, your MTGAs or whatever you're using, and then make the actual chip, the actual circuits, right? They print the actual circuits on the silicon. And in order to do that, getting back to your question, you need something called a mask set. And this is basically your cookie cutter that you cut stuff out with. And this mask set is very expensive. So for a manufacturing foundry such as TSMC, a 7 nanometer mask set is around $18 million. And this is a one-time use. Not one-time use, but as soon as you change the design, you need a new mask set. So it's quite expensive. And the lower nanometer you get, the exponentially more expensive the mask set becomes. So if you're looking at, say, like a, 28 nanometers or some older technology, you're only talking about $100,000 for a mask set. So it is quite exponential for how much mask sets cost. So a lot of times, and most of these chips that came out, I mean, maybe I can switch back to the.
So like the market's not there to justify the.
I think that's one answer. I think also, like the Sum and Over chip came out maybe 4 years ago, Graph chip 4 years ago. I mean, these companies have kind of been around.
That's my impression for GraphCore, which I've followed a bit. I mean, they developed it some time ago. And, I mean, it's complicated to keep. That's the one of these I looked at most from an open code standpoint, which is different than a hypervector standpoint. Because at first I thought you might really use that for open code pattern. But in the end, it seemed it was very optimized for floating point operations on graphs rather than for a lot of discrete operations on graphs. So yeah, not surprisingly, when you dig into these things, which ties in with Rachel's point on her own chip design, when you dig into these things, they sound like they're doing something very general. And when you look what they're actually optimized for, it's something very, very particular, which is not a terrible shock, right? I mean, that's what happens when you make custom hardware. So like you end up wanting like one custom chip for like graph convolutional networks and another one for open code pattern matching or something, right? Which is a pain, but not as big of a pain as it used to be.
And these are all digital, right? It's not an analog. Like my friends over at InMemory Computing doing the memristor stuff. That's a whole different world because they're trying to do more analog stuff.
These are definitely all digital.
Oh, yeah.
Yeah, so the memristor stuff falls into this processing and memory paradigm, right? So JJs, MTJs, these are considered memristors.
Okay.
There's another intuition for why maybe they haven't moved on that stuff. And yeah, I think time is mostly it. But also, so TSMC, just in 2021, they were talking about how much it would cost to transition to a 2 nanometer processing facility. And it was around $20 billion to build that. So as we get smaller and smaller, it gets more and more expensive to physically do these things. But you also have to account for, inflation or economics.
And I guess you can't sell GPUs fast enough, right? So all the energy is on the GPU side.
So that's an interesting point I didn't really touch on. So some of the things that GPU is SIMD, right? Same instruction, multiple data. Whereas many of these chips, especially GraphCore, is MIMD. I think the Meta chip is MIMD. But the advantage here of having MIMD is that you can process a lot more complex operations and programs. And NVIDIA, for reasons we could speculate but won't do so here, has never really tried to optimize power usage. And so one of the things that we're seeing, which is kind of my point with ChatGPT's $700,000 a day running cost, is that because you're just throwing massive amounts of GPUs, you're just throwing massive parallel compute capacity at these problems, and they're power greedy, they cost a lot of money to run over time. And this isn't sustainable. That's my opinion. There's some data to support how not sustainable it is, but that's, that's a longer talk. Maybe we can get into another time.
We're touching on a point that I wanted to ask.
A little bit louder.
You were touching on a point that I wanted to ask about. So all of these are measured in floating point operations,
Uh-huh.
but if you move to memory, you could use a different operation as your basic compute operation, like the APU of the GSI that we were talking about yesterday, right? They have a different set of operations.
Yeah,
So
yeah.
Can you say more about that?
Yeah, so all of these are just like standard deep learning accelerators. They're yeah. So they're not doing too much interesting, which I think was kind of Ben's point of like if you look at what they're actually optimizing, I mean GraphCore, kind of what they've done here. And they're a wonderful company to work with, and they have some free cloud compute. So I'm not by any means bashing what they have, but basically what they've done is they've taken a regular GPU, which was made for graphics processing, and really excels at graphics processing, stripped out all the overhead, and what you're left with, plus some special sauce, is a GraphCore IPU, right? So that's why all of these show floating point. And one of the points that I've made on here is kind of the bit architecture that these things are made to compute in. So like Meta has 16-bit, GraphCore 32-bit, but I think they have a mixed precision now. And then Cerebrus 32-bit. So this kind of floating point architecture goes away when you get to some degree processing and memory, right? And I will touch a little bit more on like how the precision of floating point relates to processing and memory, kind of very shortly here in the next talk. But the main idea, and which is why I spend a little bit of time talking about analog computing, is that in analog computing, what you're basically getting is like this very large information capacity, because you can continue to divide like a wave signal, like an electronic musical wave signal or something in a musical synth, which is also an analog computer, or circuit, or however you want to call it, right? You can continuously divide this wave infinitely, right? I mean, theoretically, it's infinite compute, but it's not actually, right? And in digital, what you have is precision, right? So you're forcing a 32-bit representation, right? You're decreasing. You don't have infinite ways of parsing up this wave before I run into this thing. And then, so what kind of the trade-off is you're trading off information capacity for stability and precision in digital computing, right? And so kind of the intuition that I'm trying to build here is that maybe for AGI or more complex learning algorithms, which we'll shortly talk about here in a second, you kind of want something that is merging this idea. You want something that is not just saying 32-bit, 16-bit, 8-bit, right? You're not trying to be so discrete. You want some sort of continuous representation of input space, but you want it to be reliable in the sense that like you can still compute stuff without having to say, okay, it's the answer is 2 this time, but next time you run it, it might be 3, which is something that happens in weak analog computers, right? So does that answer your question at all?
Yes, sort of.
Okay.
I was hoping for example instruction sets, but maybe we'll get that later.
Yeah, I think it's a little more time than I had originally planned for. But
We have
Right.
one comment from YouTube real
Uh-huh.
quick. They're saying that I believe Tesla also has their own chips, Peter Van or Tradeoff.
Yeah, that's absolutely right. So, where are our slides?
I stopped your screen share so we could watch you.
Oh, okay, no worries.
But
Sorry. I just got nervous. Yeah, no, so lots of companies have their own chips. I just put a couple of the main AI ones on here because everyone's been talking about LLMs and yada, yada. And I wanted to kind of show how they're all basically very similar, right? They all have a little bit of their own flavor, but they're all kind of the same thing. The Tesla chips are interesting. I mean, basically what everyone's doing at these large corporations is taking their tech stack and then making these minute kind of nuanced little changes to make it work specifically for their tech, their software stack, which is great. I mean, it's Tesla cars are a certain flavor of things. So yeah, was there a question in there? Was that just a comment from him?
Comments.
Okay, all right. So if there's not any more questions, I might switch gears talk about stimuli, zone flavor. Oh, goodness gracious. Oh, no. Okay. All right. So there's our startup stimuli, which Ben Gertzel and another guy, Benoit said, have all helped co-founded here. And the idea is that we want to make accelerators for AGI. We want to be able to capture all of the math that can lead to more intelligent computing machinery and algorithms and software systems that have been left out of this deep learning GPU revolution.
Are you sharing?
Am I sharing? Yeah.
Not yet. Can you reshare?
Oh, it says stop share. So when it says thinks I'm sharing.
Thanks for sharing.
Yeah, it thinks I'm sharing.
See. I don't see a share from Adam right now.
I'm trying. Hitting the stop button and it's not doing the stop. So I don't know.
It's just Apple.
It's just, I'm one for.
Yeah.
Ring.
Good to go. Okay, awesome. All right. Okay, so my name is spelled wrong, but it's down here at the bottom, Rachel St. Clair. The C on my keyboard quit working this morning. So, anyways, so kind of the idea is we're trying to get to this like AGI motherboard sort of super intelligence platform. Don't set me on fire. I know it's a little bit of a heretic to say super intelligence here, right? But I have this pretty chip picture. So you could imagine sort of a motherboard which has very fast interconnect between different dedicated processing chips. So you could have a GPU on there, you could have an IPU, you could have a hypergraph pattern matcher on there. You could have what we're going to talk about today, the NDEPU on there. And then you could kind of do this mega orchestration of computing for intelligent, AI systems and stuff like that. Anyways, I mostly just wanted to show off my pretty pictures. So, one of the chips that's being developed by Simulise is what we're terming this mouthful, nonlinear decentralized processing unit, or NDEPU. So if you think of the GPU is a little bit general in the sense that it can process graphics, and then it can also do things like backpropagation. It's just a massively parallelizable SIMD architecture. Whereas the NDEPU is somewhat general in that it's meant for large data processing, but it uses a different underlying structure. And that structure relies on fixed point processing and memory kind of architecture setup in the hardware. And the idea, the reason why we want to build this chip is because I want to be able to have AI which can scale, right? Which can scale efficiently, and that when you want to learn new things and when you want to increase the capacity of the model, you don't just buy more GPUs and slap them on the data server, right? I want things that over time, as you're learning more information, don't become more and more power greedy and don't end up costing more and more to run. And one of the benefits that falls out of this is that things become more decentralized. So this fits very nicely into Ben's kind of distributed, decentralized computing scheme for AGI. Because I kind of touched on this earlier, but if you have, whoever has the most compute resources has the most AI power, I don't know. It's just not the flavor of AI that I want to create. Like, I want kind of everyone to be able to contribute to AI and not just be whoever has the most money to buy the most servers. So that's one motivation. The second motivation is I want to be able to have general information processing, which is a very vague term. I know. But I think we all maybe kind of have an intuition of what general intelligence is, maybe. And the reason personally, kind of my motivation behind why generality is needed, or whereas in some cases you want speciality like protein folding, deep learning all day, right? But if I want to take kind of fields of quantum physics and kind of formal structures and poetry and create a brand new field, right? If I want to do kind of this extrapolation or this ability to really synthesize new knowledge and learn new things about the structural reality and natural furniture reality or something like that, I suspect maybe we need general information processing, right? And I think this might be good because it might help humans a little bit, but these are kind of more speculation and opinion than they are fact. These are just motivations, right? And then also, I want to work on kind of a different architecture than is currently being worked on because it's cool. Because the architecture I'm working on sounds cool. It sounds cooler than deep learning. So that's just a personal motivation. I just want to separate that from scientific fact. But who knows? It's very early, but it might lead kind of this, rather than just being cool, it might lead to things like more beneficial AI, more controllable AI or something. I mean, I don't know. This is just opportunities that have yet to be explored, discovered, right? So I'm not saying I have it all figured out, but I'm saying there's some interesting stuff at play. So I'm very interested in learning algorithms, right? If you've heard me talk at all ever before, you've probably heard me harp on backpropagation, which I won't go into here. But what I am going to say is that I'm interested in learning algorithms and new learning algorithms, ones that scale, ones that can do general information processing, and ones that are cool, right? And maybe have other features like, good AI ethics or controllability or like, other principles we may want in AI, creativity, things like that, emotions, maybe things like that. So there's 3 principles that I am focusing on building, that we're focusing on building. And I'm saying all this because eventually I'll get to the sentence that says, this is why we need a new chip. So just bear with me till I get to that point. But one of the first things is this idea of separation. So all these ideas I'm borrowing from this guy, Andrew Coward, and that A is not supposed to be there. It's a typo, sorry. But Andrew Coward, he has this new book called Brain Mechanisms. It's absolutely fantastic. It's a lovely book. If you want to understand the brain and higher cognition in terms of something like anatomy or physiology, this is the book. I love it. So anyways, that's where most of this stuff comes from, but I'm boiling it down very simply for the purposes of this talk. So there's these 3 kind of minimally necessary criteria to implement new learning algorithms based on Andrew Coward's model of understanding how the brain works. And I'm going to use kind of neuroscience terms here, but you want separation. So the thing that is learning the features should not be directly updated, directly optimized by the thing that is making the decisions, right? So this is what deep learning does currently. It does the opposite of what I want, because you have backpropagation all the way down to the earliest layers. So the earliest layers are now being tuned to the sake of the current task, which means that whatever they learned for prior tasks is getting overwritten, right? So you're continuously moving the system toward the new optima, which is great for specific learning, but you're degrading prior learning, yada, yada. So a better way to do this is to just sever these 2 things. So in the brain, we have kind of the cortex, which does this feature learning space. And then we have subcortical structures like the basal ganglia, which interpret the abstract firing patterns of the cortex. This is why it's called recommendation architecture. And the cortex recommends a behavior based on abstract firing. So I like to think of it as like abstract artist paints abstract art. Someone comes into the gallery, looks at the art and says, oh, I think this means to be sad or to be happy, right? And then there's some other processes that say, oh, you interpreted that correctly or incorrectly. But the person interpreting the art does not go tell the artist, oh no, redo this, right? They're just viewing the art. So that's kind of the difference here. The second learning algorithm has to do with synaptic plasticity, which I think a couple people have touched on over over the course of this talk. But the idea is that you have pruning and growth. So by the time you're like, we'll be very generous, by the time you're 5, your brain and where the neurons are and how the neurons are arranged have somewhat solidified. But what continues to change over your entire lifetime is the connections between these neurons. And in Andrew Coward's understanding, which is the neuroscience literature I'm subscribing to, this is a mode of learning. And this is a mode of adaptive learning. And it has to do with sleep and things like that. You get into weeds of complexity. But basically, we want to be able to change connections of how information is transferred, right? We want to be able to change the little race car tracks for which information flows on, because that way we can route information to other information and have new ideas. So I like to think of it as like Lego pieces. So you get really good like combinatorial expression out of a system for which you can combine almost infinitely in different ways, all these different Lego pieces. So how you can connect all your different segments of information, you get more expression out of a system like that. And then the last but not least is self-activation, which is like pretty cool. So this brain has the capacity to say, okay, I've never seen a penguin before. It's my first time at the zoo. I'm a little kid, maybe, or maybe I've just never seen penguins, but I've seen other birds. And so there's neurons in my brain that are firing to say, okay, I see beaks and I see like these little flappy wing kind of feet thing that look like birds. And I see these kind of like flappy things that maybe are wings. So there's a population of neurons in my brain which are like trying to compute to the answer to say that penguins maybe are birds too. But since it's something new, I don't really have the capacity to fully complete that computation. So there's neuronal circuits in my brain which will actually self-activate the rest of the population, which describes bird category in my brain, to say, okay, include these new neurons plus activate this bucket, fill this bucket all the way up, and now I can say, is this penguin a bird? Right. So that's the idea of self-activation. And in order to implement some of this stuff, some of these new learning algorithms, there's this idea, not this idea, but there's this circuit in the brain, right? This hippocampal cortical loop. And I don't want to go into too much neuroscience detail, but basically the principles of how the synaptic plasticity and the self-activation work rely on this sort of record of simultaneous pass firing, right? So when you're doing self-activation, which I know this is quite hard to see, but self-activation is over here, right? What you're doing is you're saying, okay, I have maybe some visual inputs and I have some auditory inputs, and these things are, they work together because they're occurring at the same time, right? So I see, well, let's go with the dog. So I see a dog and then I hear barking. So these things are correlated. So I have auditory cortex neurons which fire and then visual cortex neurons which fire. And I need some way of knowing, if I'm going to implement this in software, I need some way of knowing that these two populations fired at the same time according to X stimulus, right? It's a very naive way of implementing this as a list, which you could probably see is absolutely just terrible, right? So just every time you get an input condition, make a list of all the neurons that fired. That would be absolutely horrible. But you need something like this in order to implement these new learning algorithms. And so we want to use, and for other reasons, this thing called hyperdimensional computing. It's super awesome. It's a type of mathematics that came out in around 1980s by this guy, Pentti Kanerva. You've probably heard me harp on it before. But essentially, we're not using matrix multiplication. We're not using, well, we use tensor products, which is a driving force, but we're not doing back propagation in these new learning algorithms. What we are using is this hyperdimensional AI. And so I only got like 15 minutes left. But so one of the things I did want to touch on is that, so kind of what a lot of people are doing right now in regular AI, this is not including, Hyperon or many of the other projects, AI Go or, NARS, it's not including that stuff. This is regular deep learning. What they're trying to do is they're trying to reduce the precision of the architecture into something like 8 bits, and most of them are at mixed precision and like 32-bit, 16-bit floating point architectures. And they're trying to get it down to be able to represent information sparsely so that you use fewer computations, but you get the same accuracy. This is kind of the core idea. And what hyperdimensional computing does, what we're trying to do, can almost be said to the effect of that we're trying to use fewer than 1-bit representation. I know this sounds crazy and you're all looking at me like, this is magic, not possible. But it's pseudo-quantum. So if you think of a quantum computer, you have these qubits, and these qubits represent, a single qubit represents more than one single part of information, right? And so it's the same in hyperdimensional computing. You have these things called hypervectors, which is very long bit vectors, but they could be any real valued vector, integer or complex. I said real value. They have to be any integer vector, real or complex. And essentially, there's all these cool properties that fall out. It's robust to noise. You need fewer training loops. There's a prototype paper which we put out this past year since the last conference that touches on this fewer training loops idea. There's less data orchestration. It's really good at taking raw signals, converting them to hypervectors, and then just running with that type of process. There's all this really interesting stuff. But we use fixed point. We don't use floating point. It's all binary Boolean algebra. So the idea kind of behind why a chip and this hyperdimensional computing stuff might be cool is that since you're using fewer bits, this is core idea, you're using fewer bits to represent the same information, you can put more information through this, assuming you do everything else right? Big assumption. You can put more information through the system at once because you're using fewer bits to express the same information, right? So per number of bits, more information is going through. That means higher throughput, which means increased speed of processing an entire program. And then you naturally get reduced power as long as you don't mess up all the hardware and the other stuff because you're using fixed point architecture. And fixed point architecture, there's not as much overhead for all the floating point nonsense, which, don't fire me for saying nonsense, but nonsense. So it's less power, right? Yeah, there's some interesting stuff on compression here. And I know there's a lot of mathematicians in the room. So it's more of an encoding, right? It's not quite compression, but you can think of it as compression because if you do some funny stuff, you can essentially compress your information into this encoded hypervector form, and then you can compute in this compressed form or compute in this encoding form. So this is kind of the core ideas behind hyperdimensional computing. So I'm just very quickly going to go through some of Simuli's kind of like hardware preliminary stuff that we've looked at. And just because I know you guys are like, oh my God, tell me more about hypervectors. I'll just very quickly show an example here. So this is an image of a unicorn. It's a PNG image, which hopefully we're all familiar with, like .png. The number of floating points, the binary representation of this thing in a 64-bit architecture is 11.8 million bits, right? And it comes in this three shapes. So you have rows, columns, color channels, which has 4 because there's an alpha because it's PNG. And if you turn this unicorn into a hypervector, you can do that with 10,000 bits and still losslessly recover this unicorn. And it only has one shape. So if you're thinking about shuffling data around on a chip, do you want to shuffle this 3D cube or do you want to shuffle this 10,000 bit string? That's kind of the intuition behind like where this stuff might be useful for increased performance gains in computing. And I'm not going to go over this slide, but there's some interesting math that's associated with hypervectors. Our esteemed colleague here, Peter, is going to touch a little bit on like what actually are hypervectors instead of me just talking around the issue the whole time. But you get this neat thing called like the holographic effect, right? So if you're familiar with how holography is made, holograms are made, you get this wave interference pattern. And then from this small part of the I can't say that word, the photolithograph paper, right? You guys know what I'm talking about. If you take a little section out of the paper, which has captured the wave interference of light of the lasers, you can still recover the entire hologram. And so there's a similar property in hyperdimensional computing, is that you have this huge hypervector, which is capturing this wave interference pattern, which is kind of gets back to this like analog digital information capacity for precision kind of discussion I've kind of been getting at here. You can take a small section of the hypervector and still infer properties about the whole of the hypervector. So there's this kind of part-whole relationship. I know that's kind of a lot to think. But there's also another cool thing about this. It has a little bit of a natural immunity. So if you look into XOR encryption schemes, that would give you an intuition about like the immunity, which I've touched on here. And I've just done some back of the envelope calculations, which we could speculate are more or less accurate based on like D-Wave's compute capacity. Just for that one unicorn image, it would take basically all of D-Wave's compute capacity to decrypt it if you used hypervector and XOR encryption scheme. But this is a very loose calculation. So the method for this NDEPU chip is that you have data and you have instructions for what to do with that data. And you send that to the chip, goes through some Cheeto compiler, and it converts your instructions into hyperdimensional operations, right? H2C ops. And the data gets encoded into hypervectors. Everything that hits the chip turns into a hypervector. And that encoding process, depending on how you do it, there's a way to do it which is data agnostic. It may not be the best way, but there's a way to do it just byte by byte, straight bytes. And that encoding process has these bottlenecks, like a majority function. Sorry, I thought maybe I had to sneeze. And a permutation. And these operations are expensive on traditional hardware. So it might be worthwhile, we think, to develop new hardware to kind of make this entire process faster, right? And low power, so it's cheaper, getting back to the motivations and all these things. Anyway, so you turn into a hypervector if you're a piece of data, and then you get computed on, and then you either get sent out off the chip if you're doing some sort of AI stuff, tell me what to do, which way to drive the car, or if you're doing maybe database processing, which is distantly in the future. There's some foundational hypervector research that needs to be done before you can get to that point. You would decode. You would losslessly decode as possible and get back to the original data. So the degree to which you can compute in this form is heavily related to how much of the original data you need back versus the pure output you need back. Anyways, this is kind of the main idea behind the chip. So we did some very early tests, very early, basic, just super simple. Is this even worth looking at tests? You take about 2,000, 3,000 images. You send it to a single processing core and a CPU. And then we have an FPGA implementation that does this section. So just the send data, encode, send the data back, decode, send the data back. It doesn't do the compute. So we have an FPGA implementation that does everything but this compute part. And we compared that to just regular CPU and GPU for like data sharding, compression, comparison. Just very simple tests, not at scale, right? And, oh no, wrong button. And we get really interesting results. I'm not going to spend a lot of time on this because the tests are very simple. But basically, we get back to kind of this idea. This idea is kind of what we see. Higher throughput, increased speed, reduced power. Okay, so the chip itself, we're actually still looking at nailing down the exact architecture. So personally, I really like Joseph junctions and superconducting stuff. It's really cool. But memristors give off a lot of heat, which means they have to be cooled. And cooling, keeping things at 4 Kelvin is very expensive currently. So if I had it my way, we'd be doing JJs all day. But we're not doing, it's up in the air. So currently we can either have something like a system on a chip. So you have a bunch of different chiplets. They can be heterogeneous. Oh, thank you. I appreciate that. It's very fun. So you can have kind of this heterogeneous chips, which are all specialized logic units to compute certain information, right? And you can put them all together on some sort of fabric. This is what all the cool kids are doing. They have this near memory fabric. And you can route information through this way. It won't be non-volatile, but it'll move data very quickly. And we would use regular kind of CMOS, MOSFET processing technology for that. Or we can kind of do something as NDEPU in a system. So you can just use kind of this like CXL architecture, which is this Micron or MicroStrategy. I'm blanking on which one it is, kind of data highway to route information along. So you can have several different, maybe a GPU, maybe an NPMC, whatever, NDPUs, and you can route information between these things. So this is kind of core idea for hypervector. I mean, for the AGI motherboard. Yeah, so basically, we don't really need to look at this slide, but basically what we're kind of looking at is which processing and memory framework we want to use. Do we want to use near memory computing, which we're using kind of a CMOS fabric, or do we want to use something like just really cool new stuff like superconducting JJs and make it fully innovative? So that's what we're looking at now as we're getting into the architecture stuff. We're focusing on kind of some software that will be able to run on the chip, because even if I gave you guys on an NDEPU right now, you'd be like, neat, it looks shiny, but what can I do with it? What can I run on it? So we're looking at some kind of rudimentary, maybe AI softwares to run on it. So if anyone wants to collaborate and think about what kind of AI softwares you might want to run in HTC space on an NDEPU, let me know. Yeah, that's it. Thanks for listening. Maybe we'll have a couple questions. Oh, I finished with 2 minutes.
Yeah.
So maybe we'll have a couple questions, and then I'm gonna let Peter take over, and he's gonna really jump into HTC.
But if we take a couple questions, we'll have a small, quick
Yeah,
break.
we'll take a
and
break.
come back. And Peter?
Thank you.
This is more of an application question.
A little bit louder.
This is more of an application question, but have you thought about encoding Clifford into HTC?
Like Clifford Space Algebra.
Clifford algorithms?
I think maybe someone in the room has mentioned it once or
Yeah,
twice.
we discussed it. So basically with the hypervectors, if the XOR operation is, so the Clifford algebra product on basis vectors in that n-dimensional Clifford algebra, the Clifford algebra product is XOR plus a funny sign rule.
Okay.
So the XOR operation on hypervectors, if you neglect the plus or minus, basically is the Clifford algebra product on the basis vectors, which is a cool thing.
Yeah.
Then if instead of the permutation operation, which is commonly done on hypervectors, you just pick a random series of rotations in the high dimensional space, that serves the same function as a permutation operation.
I see.
So then you can take the bit vectors as Clifford algebra basis vectors, the multiplication of the basis vectors in the Clifford product.
Yeah.
So you can pick a random rotation from the permutation. Then you have very nice algebraic identities. And we were discussing some rigidity the other night. Then they asked me, so what is the practical use of that?
Oh, okay.
And then we got distracted with other conversations.
Oh. The physics community, the graphics community, they've switched over.
Can you speak? I can hear you.
You're doing this in lower dimensions. So you're doing very high dimensional Clifford algebra compared to either normal physics or graphics. Right? So it's a more fine-grained question of exactly what learning or reasoning or memory access operations in hypervectors work better if you have the algebraic identities you get with a Clifford algebra, which seems there must be many, but I haven't followed it through.
Okay, we should talk.
I want to talk too, Max. Please, yes. So, good.
Yeah, from physics, it's you get in love with the elegance of Clifford algebras, right?
Also, the compression, you can
Yeah.
say things so much easier in Clifford, yeah.
Cool. Okay, any other questions?
Yeah, you seem to be talking a lot about designing the chips and a little bit about manufacturing the chips. And I wonder why not to stay with FPGA? Why are you actually going to manufacture?
Very good question. The data flows on FPGAs suck. Just to be quite frank, to route information around on the FPGA, so getting data in, getting data off the chip, the I/O channels aren't that great. Also, there's like limited bandwidth and like memory, so like how things can move on chip is limited as well. And so if you're moving these very large bit vectors around, it's really a pain on FPGA. So we've kind of gotten some really prototypes, but those numbers aren't super highly reliable. I don't know if you guys have ever looked at what goes into like an estimation on like a accelerator, but those numbers aren't super reliable. I mean, they're all based on like so many different factors. Yeah, but I guess the core idea is that we need something a little bit more specialized. The FPGA, even though it's reconfigurable, the core busing and data transfer system is quite limiting.
And the flexibility of this design, because you can then, each time you have a new idea, you can easily implement it on FPGA.
It's good for prototyping, but it's terrible for like large scale petabytes of data moving, like actual computing. It like the way the memory is structured is very limited on FPGAs.
What assumptions on the data you need to make in order to guarantee that there's going to be a good compressibility? If you may answer.
I think this question is better answered in the hypervector realm with
Okay,
Peter.
good.
I'll give you an intuition though. So the more so we're not breaking any, it's all Shannon information entropy limits, right? So the more structure there is to the data, the more compressible it's going to be.
Right, okay.
So the theoretical limits, just based on back of the envelope calculations, it's like 33x compression rate. You're not really going to get anywhere near that. But you can get kind of far. But the idea is that like what you're doing through turning stuff into hypervectors is you're removing noise, which is difficult for me to say because who's to say what's noise and not noise. But essentially you're forcing it into a more organized structure. And then that structure is yours to do with what you will, right? Compute on it, whatever. That partially hopefully answers, and then Peter can probably.
There's a question from the YouTube room. So Paul Berger apologizes for the long-winded question, but he says, about hardware prospects, what about perhaps less exotic than quantum-based computing circuits, but more evident looming over the horizon ReRAM, R-E-R-A-M, memristors? For example, for efficient neuromorphic learning systems of spiking neural networks. About hardware prospects, what about less exotic than quantum-based?
Yeah, so I kind of glazed over that. Thanks for your question, Patrick. Was it?
Paul.
Paul, thank you, Paul, for that question. I kind of briefly glazed over it, but we're in the phase of choosing the kind of core architecture design. With that goes some business decisions, right? Such as cost, applicability, first gen. There's a bunch of things that need to go into making that decision. But we also want to make something, because it is traditionally expensive to make hardware. You don't want to make something that's going to be outdated within a year, right? You want something that has a little bit of longevity for it to kind of continue and to grow off of. So we're not just looking at like JJs and superconducting materials and this kind of pseudo quantum, but we're also looking at things like traditional, like Pinatubo architecture, which is a very primitive way of doing near memory computation. So hopefully that answers that question. But I think I'm going to be not taking questions now, if that's okay. And we'll go to a break, maybe 5-10 minutes.
10 minutes sounds great.
10 minutes, and then we'll be right back here. So thank you guys, and I'm happy to talk after lunch.
Thank you.
guys, we're gonna get started here soon, so if everyone can maybe minimize it into hyperdimensional, shifting of data, that would be awesome. I'm just gonna go ahead. Are we live? Are we good? Okay, I'm gonna introduce Peter Suter here. He is a wonderful colleague, collaborator with Simuli. He's one of our lead developers here. So he's also at the University of Maryland, a PhD candidate. He's been working on hyperdimensional computing, which also goes by many other names, vector symbolic architectures, blah, blah, blah. But he's truly kind of a leader in the field. He has many published papers on the matter. Today, he's going to show us about how we can do efficient and robust learning. I'll let him introduce his own slides. But let us welcome Peter to give it a brief talk.
Yes, my name is Peter. I'm with the University of Maryland and Simuli. So, as you can see from my title here, I'm sort of going to talk about how you would do vision with hyperdimensional computing because it's a very interesting problem. But along with that, I'm going to give you a very, hopefully, robust breakdown of hyperdimensional computing on its own. So there's sort of a threefold goal with this talk. One is to sort of introduce anyone who hasn't seen it before to hyperdimensional computing. Secondly, to show how you might be able to solve some of the more difficult things conceptually with hypervectors, such as vision, some of these very high density signal inputs like that. And third, to show how hardware is almost essential to making some of this stuff work. And the hardware is not all there yet. And you'll see that through some of the stuff I'll talk about. So I have my outline here. The presentation, I'll give some background on hypervectors. I will show how you would, for example, encode image data into hypervector form. And then I'll show you sort of very typical ideas that people use through 2 case studies. Of how you would use hypervectors in a practical setting. And after that, I'll show you why these are not ideal, and you can improve on them with the proper hardware or proper representational aspect, which also is facilitated by hardware. Okay, so let's jump right in. So hyperdimensional computing, the 1,000-yard look at it is that it's the idea of projecting information into extremely high dimensional space. Sometimes to the point of utter ludicrousy. For example, I have the number 3, and for some reason I'm putting it into a 10,000 component space. And you would think, why am I doing that? It's a waste of time. It's a waste of energy, potentially, right? But hopefully by the end of this talk, you'll be convinced that it's not a waste of time. It's not a waste of energy. It's actually very useful for computing. Now, the idea with it is when you do this, all data becomes the same. So if I project into high dimensional space, everything looks the same. Number 3 is this particular high dimensional vector. Any computation you do with that number 3 is also itself a hyperdimensional vector, right, of the same length. And you're sort of relying on that long representation to distribute any issues with these computations as noise throughout the operations. So some useful properties with hyperdimensional computing: all data looks the same, extremely noise tolerant because of the fact that you projected into such a high dimensional space that whatever you do with these vectors is very resistant to the noise that's introduced through the operations. And probably the most important one here is that you get the superposition-like pseudo-quantum, as Rachel put it, properties that facilitate learning. So this superposition operation here is, as you'll see in a second, what actually performs learning in this architecture. And there's much more, but these are the main takeaways. So for this talk, there are many types of hyperdimensional computing architectures and VSAs in general. So I will mostly focus on the easiest one to grasp, which is hyperdimensional binary vectors. So we're talking about very long strings on the order of 10,000 bits. So 2 to some power, like 13 or 14, is sufficient. And you sort of expect that these vectors are randomly generated. And you'll see why in a second, but that is the basic idea. So to give a brief core idea about what's happening here in hyperdimensional spaces. So I have here the Bernoulli coin flip distribution. Now, why am I showing this? Well, we're talking about 10,000 bit vectors, so strings of ones and zeros, which I can model as a coin flip distribution, so just a sequence of coin flips. So what you can think about when you have a hypervector, you can think about it as how much it deviates from the expected value of the coin flip, right? And now you're probably beginning to see why the vectors are randomly generated to begin with. When you do this, you'll find that in terms of Hamming distance, there's this sort of big mound, as you would expect with any normal type of distribution. There's this big mound where most of the vectors will be close to, right? This expected value of roughly 50% of the bits being 1, 50% of the bits being 0. Now, but as you go further and further through the standard deviation, you become less and less likely to observe things like having 1,000 ones and 9,000 zeros, right? Stuff like that. And you'll see that what we're essentially dealing with hypervectors is we start off here, and as we do computations, we become less and less probable of occurring. And thus, if you're close to something in here, what's the chances of that? It's extremely unlikely. You can actually quantify how unlikely from an information theory standpoint by the standard deviations of significance. Okay, so some motivation for the vision aspect of hyperdimensional computing, just so you can sort of get where I'm coming from here and why I'm talking about it. For a lot of AI, vision tends to be where recursive dimensionality really kicks in and things become very difficult, right? For a while, without CNNs, we had issues with learning on vision-based data. But then you had the GPU come along and it's sort of, and then you had ASICs and all these things. And they sort of made this not a problem anymore. And now you can do all these lovely models that you couldn't do before. So to do vision, you have these high compute requirements. The model size quickly approaches impractical requirements without the proper hardware to handle it. And the correlation between input and output is much more difficult because it's very dense information. There's a lot of correlations to analyze, which is why you might know or have observed in the past, you often don't look at all the data. Consider a CNN, it looks at a receptive field. It doesn't actually look at correlations right off the bat from any distance across the bits, right? And you'll see why this is important to facilitating HDC to do vision, because it's the same issue, right? Okay, so as I said, we'll see that HDC is no exception to this, and some of this talk will be about how you can actually get around these limitations in a similar way to what we did with CNNs and other models. Okay, so another part though, one thing that is sort of motivating my thoughts about this is this paper right here. So this paper is a neuroscience paper. They essentially took an eye and limited to 1 degree of one-dimensional input through a physical experiment. And they noted that what data, when you do this like one-dimensional or forced one-dimensional perspective, the data that comes through the retina and comes out through the optical nerve to the brain can actually be clustered into these 10 very specific signals. And some of these are expected, such as receptive field, like things and convolutional operations happening on it. And some of them are, well, most of them actually, are very like mysterious. The researchers themselves here were not actually sure, but they were able to clearly see the clusters of these things. Meaning that the eye mechanically filters out a lot of information before it even gets to the brain. And the brain is essentially reconstructing it. So with that out of the way, that means one way of thinking about how to get hyperdimensional computing to work with vision is you need the right hardware, right? Or perhaps you need the right filtering mechanism, which these things will go ideally hand in hand if you want to optimize for performance. So something akin to a GPU maybe, or more RAM, and so on and so forth. And on the other and develop more efficient software to handle this stuff. So solutions in the hypervector setting, well, there's a lot of work, especially from IBM and Intel and NVIDIA on this stuff. Well, you know, the idea is that the software is sort of this one weird trick to get rid of the hardware in terms of the software is the one weird trick to get rid of your issues with HDC. And IBM and NVIDIA sort of does this a lot with some of their chips, especially the spiking neural ones that use hyperdimensional vectors in them. So with the motivation out of the way, let's just jump right into some of the basics of hypervectors. This is going to be our crash course in hypervector arithmetic. And hopefully after this, you'll get a pretty good understanding of it. So in the binary version of it, you essentially equip your space of hypervectors with a few operations. I'll start with the exclusive OR, which is this first one here. And it's a bitwise exclusive OR. There's some nice properties with exclusive OR. For example, if you XOR something with itself, it removes itself. Whereas if you XOR and it's not there, it's added. So there's this interesting property going on there. And you might see how that's useful in a second. The other one is permutation. So permutation here is sort of loosely defined because a lot of times what they do in HTC is they just shift the bits over, and that's considered permutation. It actually works 60% of the time. It works every time, right? But you can do a real actual permutation if you want. Now you can repeat the permutations over and over, and it becomes a sort of power of the permutation, which you can undo by taking the reversing permutation that gives you an identity once applied, and applying it when you want to go back to a previous vector that was permuted. And then finally, you have the most important one, I think, the consensus summation here, which is the abstraction of addition in this system. So how do you add binary things in a bitwise way? Well, you can think of it as saying it's some sort of an averaging operation, right? Because you can't really leave the bounds of the 1 and 0. So addition here is more so an average operation. And on average, you want to say which bit is the one that represents that component the best across all the terms. So they call this the consensus sum. There's other names for it, but the idea is very simple. You have these n terms. Whichever one gets n or more votes is going to get that value, the 0 or the 1. If it's a tie, you can do a random tiebreaker for the most part. Okay. You'll note, though, that when you have this addition, you sort of can't just like add more things to it. You have to recompute the whole summation for it to be accurate, right? So that's one thing to note. So if you want to add, without recomputing the addition, add more terms to it, you're sort of doing the structured addition where the first things in the first terms are sort of less important than the new ones. So this gives us sort of time linear in the sense of like what happened before is more influenced by what is happening now, right? Okay, so when you have this, you'll note that because of the fact that XOR gets rid of itself if it's XOR with itself, XORing this Z that's summed with some number of A's with one of the A's, the XOR will distribute across the terms. And what you'll find is that when it's XOR with one of the terms that aren't I, they become basically random noise because you have a random vector, it's XOR with a random other vector, you're just going to get another random vector basically, right? But when it gets to the I, it can't be random. Actually, it's going to be pretty close to 0 for that term. And in fact, that's what you're relying on. The statistical significance of getting closer to 0 from a standard deviation perspective. All right. So that means that this is approximately equal to 0, but from a sort of like information theory standpoint of how far you go.
Sorry, the plus there is that the plus of the XOR of or the plus of the majority, the 3C.
This addition here is the consensus one.
The last one on the slide, C.
Well, let's see.
Will C? Where's C? I'm sorry. 3C. Oh, I'm sorry. This one right here. Yes. What about?
Yes. So is that the majority or the XOR sum?
Oh, the symbol is the XOR. Yeah. And then Z is the summation you have up here. Yeah.
So I didn't get the idea of why AI XOR Z equals 0.
It doesn't equal 0, but from a statistical standpoint, it's much closer than it should be. That
Okay.
It's
I see.
if you're 10 standard deviations towards 0, it's like.
So where do they come from, these AI? Where do they come from?
We'll get to that in a second. That's, well, ideally, that's really the work where you as the designer of hyperdimensional computing spend the most time. The actual learning and arithmetic is actually very easy. So anyways, let's move on to a more complicated idea, which is how you would represent data with this, which, well, you're getting at, I assume, with your question. So let's say you have some Zeta pieces of information coming in, right? And you want to map them to hyperdimensional vectors to represent them. Well, if you have that, however you obtained it, if you have this mapping, you can do certain things with it to represent structured information. For example, if you want a set, well, you could just XOR all the hyperdimensional vectors together, and XOR is commutative, right, associative, and you can get rid of the thing in the set if you know it's there by just XORing it with itself. So you get this nice, almost the full set theory notation. There are some things that are missing here, but that doesn't really matter for this conversation. But most of what you need is there for computing. Then you have ordered pairs. So with ordered pairs, you could do something like permute the bits of the second thing in the sequence and XOR with the first thing vanilla flavor. So nothing done to it. Why? Well, this permutation here serves as almost like a basis operation where it separates this same data type from each other by by mapping it to this permutation value. It's some kind of different local space, right? So permutation preserves the mapping of distances of vectors because of that, as does XOR, which you'll see in a second. Then you can, of course, take this idea and extend it to a sequence where you can just arbitrarily permute things as you add them in. You can depermute by just taking the inverse permutation and XORing it with it, and that lets you pop things out of the sequence. And you'll note that you can pop anything out of the sequence arbitrarily. You can have holes in the sequence, essentially, which is an interesting thing. Finally, the most important one for learning here are records. This is essentially an abstraction of like an object where the R's here are the records of something, age, name, whatever. And then the V's here are the actual values that you want associated with each of those records. So perhaps my name is Peter, I'm 30 years old, so on and so forth. You can represent that by simply XORing each of the records with the values and then adding them up. You'll know from the previous slide that if I XOR this with one of the vectors I used to construct this, it'll cancel itself out. So if I have this and I XOR it with, let's say, the record name, this will cancel out. This becomes noise because it's random vectors. And this V1 here is sort of statistically significant. And then if I compare it to V1, I realize that I get much closer to 0 than I should have been. It's almost like a spike in the direction of V1, meaning it's significant. So you can recall what was in the record with that way. And of course, you could do vice versa. Given a name, can you find the record that has it, right? So on and so forth. Oh, you can also have many different things that you're looking for and search for them at once. Yes?
Just quick question. The plus is AND operation in the last thing, or is it a different operation?
This is the XOR, and this is the consensus summation. So it's
consensus
plus,
summation. Okay. And then
in an averaging sense.
and then just the permutation. Are you doing complement, or are you doing shift for permutation, or some other?
You can do whatever you want, actually. Shift, of course, you have a finite number of shifts you can do before you repeat, but you can also do just any permutation you want, as long as it's somewhat random looking.
Okay, thank you.
Okay. So these data records are very important because they can be used as a tool for inference. So suppose suppose you have some categories, some things you want to, some objects you want to recognize or whatever. And let's say you have images of them. Well, you can compute the record of these things by binding the example image with the symbolic level representation of the class, which is just a random hypervector. But the image itself is not random. The hypervector for that is not necessarily random because it's constructed from that signal. Then if you're looking for the bird image, you can XOR with some new image and see if it's close to bird. And if it is closer than the other classes, relative to the other classes, it must be the class you're looking for, right? That's inference. That's what a neural network does. You give it some data, and you can get the class you want, for example. And you can do more things, not just class, or you can do regression and other things with the system if you're smart about how you do it. So, okay. And as an addendum, of course, if you XOR with itself, it's going to be very close to 0. And that's the logic behind why it's actually the one you recognize, because it spikes towards 0 significantly. So Hamming distance here, which is XOR, right? The size of the XOR in terms of bits that are 1, that tells you how close you are to your what you're looking for. Okay. Yeah, I said this. So you expect B to be closer matched than the other ones, and that means that you can detect, given an image, what you're looking for, or given a class, you can detect the prototypical image of it. Now, what if U, V, and W here are not just one image, but many? Well, now it starts to look like a data set, right? I have this many dogs. They look like this. They're all dogs, right? This is what a data set would be. So this is the interesting aspect here. And that gives rise to what I like to call the hyperdimensional inference layer. That's not what people call it in the HDC community, but I like to call it that because it gets the point across. It's sort of like a layer of inference. So I have these broad classes, which are hypervectors represented by these yellow squares. You sum them together into some other hypervector of the same length, which is this bluer square here, right? But each of these yellow ones are actually the XOR of a random identity vector representing that class and a superposition through the consensus sum of the examples. Now, if you XOR a particular example, or maybe one that's close to the ones that are bundled together, then the things here will be more significant versus the other classes. So you can do detection across many classes this way through a very simple single XOR. The bulk of computing is done by the addition operation here. So that's the part that's training. That's the most expensive operation. Now, let's move on to how you actually get these vectors that represent the image. Well, okay, so somehow I have to generate a good hypervector that represents some image. It must be meaningful in some way to facilitate the learning and the bundling. Okay, many engineering challenges here because there's no nice way to take arbitrary images and just turn them into low order representations through like some finite thing. So a lot of the research on hypervectors is how to actually do stuff like that, right? First, let's just consider the simplest way you can encode information. You could, for example, if you want to encode just a simple integer value or continuous value, you could just randomly pick 2 hypervectors, and those are your endpoints of a number line. And then you stochastically choose some number of bits to slowly transform one part of the number line to the other. And so you get a nice range. If you do that, here in this video, you can actually see this happening. On the left is a particular value as it's going through a number line being changed. So these changes in bits are how many you change at a time. And this is the full hypervector in the square organization. This is the original endpoint. You can see it's getting more and more noisy as time goes on because you're further and further away from it, right? So these red and white squares here represent where it differs. So if you started with this number and you started moving through the space to the other endpoint, the first endpoint becomes more and more noisy because you're further and further away from it. Okay. That's how you could encode just a simple, just a simple number. Okay. And to make it more clear, here's a nice image of this is the heat map of the distances you would get. So here are the integers compared to each other, right? I let this last row be a completely random vector just to show how it looks relative to actual values that are part of this. So you can see that even the extremes of this are not completely random and detectable. You yourself as a human can detect the difference between this and a random vector. And this, of course, is the heat map relates to the distance in Hamming space. So the number of bits of difference. Why is this important for image encoding? Well, you can think of an image as a sequence of pixels, right? So simply take your number that you've embedded into this hyperdimensional number line. That's your pixel value, right? And now you just need to permute every time you want to add a different channel. So that one pixel can represent as a sequence of channels. And the pixels themselves could be a sequence of pixels. Now, of course, you have row and column, so you need two different permutation patterns like here R and C to encode that properly. So as you move this way, you permute the pixel value with C, and as you move down, you permute it with R. Okay. So in this case, permuting this with 4 iterations of C permutations and 2 in row wouldn't translate this pixel to this position. And then you just simply XOR all your pixels, and that's your image. Boom, easy. So the drawbacks, though, here is that there's a lot of pixels, which is bad. Because although you're very good at tolerating noise with hypervectors, if you have a lot of things, you could start to get confusion. Right, so this is a nice, naive way of doing it for small images, but once you get to bigger images, you get issues. Some of them I've listed here, all right? So you need better ideas than this for any real life example. So some workaround strategies. Well, we could take a cue from CNNs and instead choose some particular way of representing the information that's salient to the past, like a receptive field. So you postpone the hypervector encoding until after you've obtained features from your data, and then you start encoding it as a final step. And that does the heavy lifting of learning the features for you. One easy method, just take a neural network, have it learn how to encode the images into embeddings and use those as your basis for turning it into a hypervector instead of the original image. That way you've reduced the dimensionality to something manageable for the hypervector. So we'll go through one case study where we do this. Suppose you have these hashing networks that simply take an image and produce a hash code, which is just a little binary string. Project the binary string into hyperdimensional space by just repeating the pattern, repeating it somehow. It'll look random. And now run the networks with examples from the training set. And every time you do, take the hash codes they produce and just add them up. You will learn to approximate the network almost precisely. So my thing will work here. Oh. Let's see. There we go. So this is just an example of what I just said. So you have some pre-trained hash network. You give it training images. It produces hypervectors by projecting lower order hash codes into hyperdimensional lengths. You aggregate them together, bind them with the class that's representing those images, and get your hyperdimensional inference layer through adding again. And you have just learned to approximate the network. Very simply and very cheaply. In fact, the overhead here is running the network. The actual training of this hypervector system is like milliseconds, typically. So at test time, you're given some input image. The hashing network hashes it, gives you your hypervector once you blow it up into hypervector space. You search through your space of possible classes and XOR the hyperdimensional inference layer with each class vector. The closest one matching your class is your prediction. It turns out this works really, really well. And actually so well that these representations are so good, these hypervector representations, these models that are trained are so good that you can actually just superpose them together. So here are 3 different hashing networks made by the same authors, going in sophistication. So this last one's very good, this one's pretty good, and this one's kind of bad, early work. Despite them being so different, completely different ways of learning, completely different architectures, completely different levels of performance, if you superpose them again through an addition, by giving each of them an identity vector, you actually get consensus for free, significantly too. They'll pick and choose through consensus which features are most relevant to predict the final output. And for this example, so the best network here is this one, gets 70% performance. The other ones are worse, much worse. I think DQN gets around like 50-ish on the data set. Just by doing this simple overhead, which takes like no time at all, you've boosted it by 7%. Very easy, just with 3 networks being overlaid. And actually, the more diverse these networks are, the better this difference will be, because the more you can pick and choose from to solve your task. Here is a graph of how the hashing networks being learned, right, versus the hypervector form of it, which is in yellow. So you're actually learning the hypervectors as you're learning the network itself. And this is the F1 score of the performance. So this is DQ, and this is the worst network that we have. So you see, as epochs go on, the DQNs are not doing very well, but the hypervector form of it is already at the goal because it's a sparse learner. It's actually almost entirely bootstrapped your network to its optimal performance. Shocking.
Is any of this persisted, or is all done in RAM and kept in RAM?
Well, this is training, so the network is the bottleneck here. So however you do it for the network, that's the bottleneck. The hypervectors are just a little overhead, like tiny percentage overhead versus the network's operations. So whatever the network does, that's your RAM overhead and stuff. But you don't need to keep the vectors in memory, ostensibly, because they're randomly generated. It suffices to keep the seed that generated them, actually. And here you can see how well the hashing performs in terms of the task. So this is the number of bits of difference you need to get this F1 score. With the traditional hash networks, you have to choose the right one. Here would be 40 that optimizes your performance. But the hypervector is like already there. Doesn't need that optimization. So this is a cool example of how the hypervector network is actually much better at certain things than traditional network. Whoops, sorry about that. These are just for the other networks. This network is better, and yet the hypervector performance is already at optimal performance. Very shocking. Similarly, that was the best network, I suppose, DTQ. This is the second best. Because this is using Cauchy-Schwarz inequality, you get less of a boost because it's already sort of hypervectory, but you can still see that there's an improvement. It's time. Okay, so that's one case study. Here's another. Very quickly, I'll just go through it. Take the same idea, but use actual neural networks, not hashing networks. And instead of using the hash code that is outputted by the hashing networks, use the embedding before you actually determine the class. You convert the embedding itself, the real valued embedding, into a hypervector. Very simply, take the tan H to normalize it within a range, discretize this range with hypervectors, and then simply interpret it as a sequence of numbers in this way. And you get a hypervector representing your neural network's output. Do the same idea as we did with hashing networks by aggregating samples of the network running. And, well, you actually get improvement in performance in consensus the same way you did with hash networks. So you can also boost the performance in this way. We did this on MNIST and CFAR just as an example. And the cool thing is that you can continue iterating on this by simply figuring out which ones you got wrong and training a new model for those. So you get 100% accuracy on the original data set. So it's an interesting aspect of these hypervectors. This is just stuff I had in case people had questions about the results, so I'm going to skip through this. That's only if someone wants to see the results of our thing. But in every example, we improve versus other things like naive Bayes and the neural network itself, or linear SVM and all these other things for consensusing. And this just shows that you can use different types of models. So here they're very different models, and you still can learn something that improves them. Such as here in HDGL. So even though ResNet 34 is very good, you can still improve on it by using worse networks.
Quick question. Did you do anything like the consensus that you did with the hash networks with the neural nets?
Yes, exactly the same idea. Exactly the same analogy, except instead of hash codes, I use the embeddings.
Okay, and that you similar results where you were able to get improvements,
Yep.
or
And the more diverse the networks, the better the improvement.
What are the implications, do you think, of this approach for neural architectural search, where you have is it a bijection, do you think, where you extract the knowledge of multiple nets, you have this hypervector representation, and then maybe you want to go back because you can execute some nets, efficiently in some way, with a certain topology, whatever it is. Do you think that might be useful while we get better at hyperdimensional hardware?
Yeah, I do. I think you're spot on with that. Yeah. Now, why is a harder question. These things are somewhat mysterious in how they work, but yeah, it seems to imply that a network favors a universal representation, and so hypervectors are a good way to get a universal representation across any input stream or modality or anything. As we all know, once the information gets far enough into your brain, it sort of all looks the same. It's just processed in different areas, right? So this is also interesting that you can do lifelong learning with these things because you can just compute the sum again, or compute a sort of estimate by just adding newer terms and weighting the old ones differently. Yeah, this is just more results on that, which by the way, so now let's go to a vision example that doesn't use a neural network real quick. Well, what if instead of using a network, you used hardware that actually gets you good features? So in this paper, we basically use the DVS camera and the bent camera, which each of these pixels here run asynchronously in time. So they see at different rates, and they see differences across their receptive field. And so you get this very low dimensional sparse image that sees motion, essentially. So this captures motion. And then we took the task of predicting ego motion. Well, you would expect this to be very useful for that, right? With our simple hypervector model that I showed in the other two examples, by taking this and simply pixelizing encoding the non-zero or non-black regions, by black I mean no event data regions, you can outperform the CNN with like a few milliseconds of training time, a few percentages of the training examples. You can reach the CNN's level of performance on this task for similarly sized CNN in terms of resources. And you'll actually steamroll. It's very interesting. So a network that took 12 hours to train is sort of matched by this 1 second to train thing that can train in real time. Okay. This I just included in case people have questions of how exactly we did this. We basically turned the DVS signals into frames that look like this, which are very sparse. So they're easy to encode for their hypervectors because there's not as much data as a normal image. And this is just the pipeline of how the data would go to predict ego motion, but you already know how this would work because all I'm predicting is the angle of motion given the input image in the same way of consensus summing. Yeah, what if you wanted to actually make it fully hyperdimensional, right? Meaning every part of this process is hyperdimensional. Well, this is an example of it, where we simply learned from the hardware itself instead of using any kind of feature detection system. This is just the results if you're curious for it. It looks like it's supposed to be an autonomous agent moving through a space. So it's sort of, you can see how well it matches up to its motion in every angle for X, Z, and then the angle for the car turning. It's fairly good, and it's actually pretty similar to the network, which we have some of the actual measures for comparing these results here, if you're interested. But Point is, it does as well as a network for thousands of less computation time, and it does inference thousands of times faster than a network. So very, very good results. This is published in Science Robotics. It was a very good paper, I think, that shows how hypervectors could be used. And these are just some of the implications from I mentioned them already. Yeah, with about 500 images, you learned everything you needed. Last case study, and then we're done. What if you didn't have hardware? Well, why not just use some kernel method? Ben, Laplacian of the Gaussian. And you got salient features. And it turns out that this works very well, actually. You will get about 3% better than a neural network that has the similar overhead. We're talking about the overhead of doing Laplacian of Gaussian on an image, which is very small. So the neural network obviously can't compete with that. You still do 3% better than it can do for even moderate allowances of computation resources. And it's very interesting that this works so simply. So I'll conclude with one idea. What if you had many different types of kernel measures, or you learned a kernel on the fly, or you use the Fourier representation, you drop out the low frequency things? Food for thought. And pair that with the idea that you can merge networks together. Well, there's no reason you can't merge these features together either in a similar way. And you start to see why the hardware is pretty cool for facilitating this type of stuff. Okay, that's it. Sorry if I went over time, but that's it. Any questions? I also mentioned if you want to keep up to date on HTC stuff, there's a link here you can click on where all the people that work in the community post to any updates. So that's the for if you need it.
I think we're gonna do a couple questions if anyone has any.
Yeah, feel free to ask anything, or we can take it offline afterwards. I'll be around.
No? Okay.
Are there links to your papers at this link?
Oh, yes, that's the next slide. Sorry. Yeah. This first paper is Clair's seminal paper on this idea of binary hypervectors. This is a very good introduction to learn about the stuff that goes in way more detail than I went here. So I highly recommend reading, and these are the papers that we used in this work. I'm sorry, in this presentation.
Thank you.
So okay, first I have to admit that I couldn't understand everything. I tried to follow as hard as I could.
No problem.
But anyway, so my question is the same question I asked to Rachel.
Okay.
Because so Rachel showed really well. So we have data with a very high dimension. We can reduce that in a smaller dimension space, and we operate in that space and so on. So I go back to that question. Maybe the answer is neural network, whatever you have, but yeah, please, if you.
Yeah, just to clarify. So the question is, how would you generalize this idea, or?
No. My question is really much simpler. It's not a deep question. I'm trying to relate that. So I now I do understand the set of operations.
Right.
Okay, it's more or less clear. My question is still general. So I guess the answer is whatever you have, but.
Well, this is just the best there is so far. Much more to come, and there's many different VSAs.
Yeah, but I think my question is much simpler than what you imagine. So it's just Rachel showed, this compression and decompression phases.
Yeah.
And
turning it into the superposition and then reconstructing what classes are in it, basically.
Oh, so that is that.
Yes.
That's the okay. Yes. All right.
Yep. Very interesting. And because you're relying on a stochastic standard deviation based way of determining whether that's the class you're looking for, or it's present there or not, you can reconstruct things in a non-lossy way, actually, even after superposing quite a lot of terms over each other. I think for a 10,000 bit vector, you can easily superpose about 900 hypervectors and still recall every single one with 100% accuracy.
So on that point, it seems like that's an important area. Maybe you already have good metrics for this, but how do you know how big a vector you need given the amount of information or the problem?
Well, the answer is as big as you can manage, I guess.
Well, yeah, but the problem with that, of course, is there's a lot. It's one of the. It seems magical, right? But
Yeah.
it is the weakness. It's like, oh well, I'm gonna have to do this in low dimensional vectors, right?
So the trade-off is if you're doing like a lot of low dimensional conversions to hyperdimensional form, such as an integer, like if you're encoding integers into hypervector form, that's sort of a big waste. You could probably fit more in that conversion before you do the conversion by taking like symmetric on the data. So maybe instead of the pixel, you look at the pixels around them and you concatenate them and then you encode them to a hypervector. That would be like a receptive field, for example. So the answer to your question is if you engineer it right, any length is good enough to some level of performance. The bigger the length, the better the performance. It'll begin to top out at some point.
So you're thinking more like empirically determine what works based on whatever accuracy you need.
Sorry, there are some statistical measures. Adam can comment on this.
Yes, Adam will actually give a very great demo on this stuff, so I kind of want to give him a chance to do this. But real quick, one question.
Just what operations would be in the API interface to this?
Right. Permutation, XOR, consensus sum over a set, random generation, yep. And I think that, well, you could also say, search through the space of options to find the best match. That's another operation.
The algebra is on the whiteboard over there next to the coffee.
Yeah, it's very small, actually. But yeah, we can talk more about what exactly you need, but basically 4 to 5 API operations will do all the stuff I showed you. Yep.
Awesome. Thanks so much, Peter.
Thank you.
Oh, I'm sorry, there's one more question from online.
Sure.
Paul Berger again. What's the difference with a vector database like Pinecone mapping words to vec?
Can you repeat the question?
Absolutely, sorry. We had a question online, Paul Berger. What's the difference with a vector database like Pinecone? So mapping words to vec.
No difference. Actually, word to vec is one example of another hyperdimensional system, and it has a lot of these properties that we're looking for here. Actually, the layers of a network are also hyperdimensional in a real value sense. They have a large number of components. So there is no difference. Those are just different examples of VSA, which gives some surprising things. Like, for example, a couple papers show that LLMs are just hyperdimensional vectors, which, considering how much people have been talking about them in this conference, I think that's some salient information. Okay, so I'll let Adam take over. Thanks.
Yeah, can go ahead and share your screen. So Adam van der Vorst has been a member of the OpenCog community for a while, and then more officially brought in and helping a lot of the development, and now working especially closely with the Simuli team on hypervectors, along with other OpenCog Hyperon components.
So yeah, thanks. First of all, thanks to Peter for making my life easier, because I'm gonna do a practical session, and the better you understood Peter's talk, like, the better that will go. To get started with, if you have a laptop with you, like, open it up, go to this URL, and this will open the notebook we will be using throughout this demo, right? Anyone has any questions during the talk, please do so. Just ask them during the talk. This is like way easier to address because we are gonna cover a few different topics. If we can address the questions locally, then we don't have to jump around in our hyperdimensional space. right? So the intro to hyperdimensional computing I will keep extremely brief, but focus on like the relevancy here. So a hypervector acts like a vector, which means you can do some arithmetic on it, and the arithmetic that's relevant here that maybe like is a bit more alien to the standard construction is that if you want to take the center or the center of gravity of a few vectors, this is actually is very close to the majority. And you can also like move a vector in a certain direction by a little bit by adding another or like XORing another vector to it that highlights the bits you want to flip. And I will parameterize random here with like a fraction sometimes. So I will use rand, R-A-N-D, for like the general, this is a proper hypervector, Bernoulli 0.5 distributed, and this to indicate like we are just nudging the vector a little bit. And this has some interesting connections to sparse distributed representations, which use like very sparse hypervectors. Right. It behaves also like a symbol, which means if you just take a random hypervector, which hasn't been constructed in a special fashion, that it's opaque. It acts like a symbol, and you also have like your permutations. Random permutation can also kind of act like an opaque operator over these. And then finally, it acts like a graph. Specifically, the distances act like a graph. Because it's so high dimensional space, like all your intuition from like low dimensional distances fades away. And it becomes more of a question of, are these not unrelated? So are these not random, like, don't they behave like random hypervectors? Because if they behave like random hypervectors, like they don't share any structure or any relation. But if they are not, they are likely come from some majority operation that brought them closer together, right? So XORing can be kind of seen as pulling things to somewhere. Any questions?
I just
Yes.
yeah, you're standing.
I think this is fine. This is fine?
Thanks.
Yes, awesome. Right. Okay, so we will go over 7 paradigms of reasoning. This sounds really fancy, but we are basically just going to play around with the algebra, right? Figure out what we can do with it. But before I do that, I will like cover for a brief second, like a few of the operations that Peter definitely mentioned, but I maybe like can put in a relevant light here. So at some point he showed like he said like, oh, like it's like coin tosses, it's Bernoulli distributed, but showed like a normal distribution. Like why is this, right? It's because if you do many coin tosses, like if you do like multiple coin tosses, it becomes like a binomial distribution. And if you are in hyperdimensional space, so you're doing like in this case, we will be working today with 8,192 dimensional hypervectors, then this can be approximated faithfully by a normal distribution. And the normal distribution will be kind of our golden point to refer back to when we are talking about distance. So how many standard deviations are things apart?
Is there a fundamental encode and decode function to encode some string or some vector into the hypervector and then decode going back out?
Yeah, so there are many embeddings, and there is one universal one which says for each piece of information, just take a new random hypervector, which you can see as a hash, right? So that's like a universal one that doesn't carry any of the structure of the underlying data. So yes, and that's a universal one. And then your universal decode is lookup. Lookup okay. Similarity to this vector. And in fact, we can see that here one of the embeddings is random, which as a forward pass gives you the hypervector corresponding to the x, or it makes a new random hypervector and sort it. And in the backward pass, it goes over the hypervectors. It calculates like the bit error rate, which you can also think about as the Hamming distance. It looks for this closest one and it returns it, right? Cool. So let's get to this, which the link should have pointed to. If you want to get the slides, it's the top link here, although they are not much more than what you already saw. So first of all, I'm going to be using like a kind of a niche library I'm developing for specifically this purpose of using Boolean hypervectors. I think their math is the most elegant one, and you can optimize this a lot by bit packing and vector optimizations. And yeah, let's get started. So the first paradigm we're going to talk about is generalization by factoring. If any of you have read Linus's paper on sheaves, then this example may look familiar, which is that if you have some symbols, like marry and home, and some actions, which are also symbols, and you have some data points that you observed in the world, like Mary walked home or Mary ran home, then you can take these data points and use the bundle operation, so the majority, to get them together, right? Once you do this, you see that this is actually not unrelated to having Mary and a transportation, like a transportation abstraction, and then home. So, and the transportation abstraction is here, like the other ones. And there is even a stronger property that also holds. And let's actually run this throughout the demo. That will be easier. So I can do crazy things like live codes. So what you can do here, what you can say about this, is that in this case, even a stronger thing holds. Namely this one. So the assert throughout will say that this proposition is true, right? So we can see that the majority of the data points is exactly the factored out thing we expect. Any questions about the reasoning paradigms? Please ask, right? Next one, reasoning by analogy. This is a really powerful one, which I've heard this mentioned on the conference actually many times. Like, oh, we will do this by reasoning by analogy. And at first I was a bit skeptical, but actually it scales a lot better than I expected. So we will be doing the dollar of Mexico example, which says that if we have 3 fields, name, capital city, money, and we have a few instances of that, namely United States, Washington, DC, and dollar, and Mexico, Mexico City, and peso, then we can make the records exactly as Peter describes, like this, and then we can bind the different records together. Right? Now, different stuff. So this should hopefully run, yes. And then the dollar of Mexico, we can ask if we have a bunch of records, what is like what's the thing that's like dollar in this analogy bundle? So we have the USA and Mexico, and this is like contrastive, asking like what is the analogy of the other records of dollar, and we can see this the result here. The result here, dollar of Mexico, is not unrelated to peso, and more importantly, the Hamming distance. So can think of it as any distance measure. The Hamming distance of dollar of Mexico to peso is smaller than dollar of Mexico to dollar. Because, well, the correct one, if you do a lookup, the correct one is indeed this one. So let's see that I'm not a liar. You can do the same thing with something different. Like this was a currency of the United States, and that is the capital city of Mexico. And you can get the analogy here too, and it works in the same fashion. Right. Let's get to a slightly more difficult example. So here we have a few symbols, and I've related them on purpose. So you can imagine there was some different encoding that made them similar. For example, if you're querying your hypervectors from some language description, it may happen that unifocal and bifocal are similar to each other. In this specific example, bifocal is about a fraction of 20% of unifocal. And the same thing is here with round and flat. Then we have some more properties here. And finally, we state that a circle is a shape, it's flat, it's round, it's point symmetric, and the focus is unifocal. And we can do the same thing for an oval in a respective fashion. Right. Let's now define a proposition. So like a bunch of properties that we want to hold. And you can see them here. I won't go over all of them. It may be worth pointing out that this one is the selection of a record, like Peter describes. So here, this is selecting the focus from the oval, or selecting the focus from the circle, and doing the same thing as here, namely asserting that a oval is more bifocal and a circle is more unifocal, right? And so if we instantiate these, then we can see that this property holds for our instances we created. Moreover, and why this is called transporting by concept, if you have something that applies to your objects, and I will take the example of being in space. So you say your circle is in space and your oval is in space and everything is in space, then the same proposition should hold as long as being in space is orthogonal to the things you're dealing with. Right? And if I run that, then you can see that the proposition still holds on the while all the points were moved, which is quite remarkable, but because you can see that circle and a circle in space are unrelated to each other. So they are very far apart. But the relative distances are maintained. So it's projecting like a bunch of things that come together in a certain way to like the other sides of the space, like unrecognizable far, but keeping their relative distances. Right. Let's now do something like a bit more machine learning. And what we're going to do is we are going to take a circle in like a unit circle in the square of like -1, to 1, 1. Sorry for using like screen coordinates. Yeah. And the way we are going to encode it is we are going to encode each quadrant, like top left, top right, bottom left. And we are going to use random select. Select just boils down to like XOR and AND. And the random is what we saw before with the epsilon. Namely, you can like choose a fraction you want to be this or that. And this lets you interpolate between top left and center, between top right and center. And so you can encode your X and Y coordinates in this fashion. Finally, we bundle together, like we did every time before, we bundle together our two data points. So let's try and run this machine learning with 20 samples that it gets. So this you can see as your training data, but your training will be one shot, right? You will be just creating the network like with a deterministic function from its inputs with the majority function. So this is the generation of the data points. It's not interesting. This is interesting. So you're creating a sphere prototype. What does your stereotypical sphere look like? And you're creating a rest prototype. So what does the rest of the space look like? And of course, the former is generated from the positive examples, while the latter is generated from the negative examples. And then we do the same thing as we did before with calculating the Hamming distance from the point. And this time, two different prototypes, seeing which one is closer, and adding them to the relative category. And you can see here, like we get like proper generalization and some accuracy on this problem. Right. Any questions about this one? Because this is quite like there are reasons you should be asking questions here. Let me put it as one. Yes.
Less of a question, more of a point, is to know
Yes.
that train accuracy and test accuracy there are very close.
Yes. It's only 20 samples, so here they got 16 out of the 20 right, both in test and this is kind of because of the encoding that it generalizes really well. You can perfectly make encodings that makes it generalize really poorly. So this is kind of pushing the modeling outside of the hypervector world. So the same as with some other things. If you want to compress data, you need to model data, and compression is kind of like embedding it into the hyperspace. And what we are doing here is we are doing, I'm not going to say clever because it could be still improved in many ways, but a non-naive encoding as to give you some discriminability. Of course, you could make this an entirely trivial problem and get 100% on both all the time if you choose the polar encoding, right? If you did polar encoding on the X and Y, I could have cheated here and get like 100% every time because there was nothing, like it would be a linear problem. It would just be that if the R is larger, namely the hypervector in the interpolation is closer to the one hypervector, or like over the one hypervector, it would be outside of the circle and under the one hypervector inside the circle, right? Yes.
Could you recall how the encode function works? Encode XY.
Yes. So like.
Oh, it's here. Oh, I apologize. Okay, I was just looking somewhere else. Yeah. Okay.
So you know the quadrant, right? Or the different quadrants.
Okay.
And what we are basically doing is, if this is our X, and this is our Y, we are doing here the checks if X is greater than 0. So if we are in like this half, and then we are selecting like how close to do it in this axis, right? And we are doing the same thing for the Y thing in this plane,
okay.
And then so we are embedded. Cool.
Okay, so you're doing that, but across. I mean, you could, yeah. So okay.
Like while embedding in general, like, but for this talk, it's not super interesting to go deeper into the embedding. But in general, embedding is like really important for doing hypervector stuff. And some things embed almost trivially, for example, floating point vectors, you can like embed trivially into a higher dimensional binary space with like the position you want. And embedding integers, like yes, you're inflating it a lot, but you can also compress them a lot back by taking like majority. But for everything else, there is some in between, right?
Yeah, I mean, the thing that is puzzling me, I mean, well, too many things are puzzling me, but which is, but the thing that motivates me to understand embedding is I mean, encoding, I guess, is like how the, like over what features majority is working on, because it's, I mean,
Right. So that's actually a good question. The features it's working on here is like the centerness of a point,
right,
and then a combination of either the top leftness and the bottom rightness, or the bottom rightness and the top leftness. Like it's interpolating between these sectors.
Yeah.
Makes sense?
I see. Thank you. Yeah,
Okay.
I understand.
Yes.
For me, the only thing that is a little bit confusing. It's like we have two levels of language. You have the domain definition, right? So the domain problem itself that you want to encode, and then you have the manipulation that's happening, or the storage operations underneath.
Yes.
So it's hard to kind of separate out when you're putting them together.
That's absolutely fair.
So I mean, in the future, what would be helpful is if you have just a declarative domain language. It could be JSON, it could be something else, where you take, you know, the items of that you're describing in the domain.
I see what you're saying.
Encode those, and then you have the manipulations going on underneath to actually.
This is the same like static topology thing that was talked about with like GraphCore. Like you can absolutely embed the hypervector operations, like you can streamline them, you can compile them into something like really efficient. But often you want some dynamic nature, and it's actually useful to have like a general purpose programming language to call this in as a library. So there are like two kind of opposing views of a specialized component here, and it as an accelerator, where you're sending some tasks, namely the hypervector computing operations. Specifically in this library, what I actually did was as you can see here, I have a few NumPy implementations. Like this is packing 8 bits into bytes and using that to do the operations. But I also have a symbolic implementation, which can run the same code, but if you run it, it just gives you like a new object back, right? What you can then do, if you have like in your dynamic language created your domain specification, you can then compile this down to code. So you can, first of all, do transformations to them, like optimal sharing, and then you can execute them with your favorite implementation after the fact. You can store them, or you can export them as a Python program or export them as a C program. So there is a certain separation depending on how much of the dynamic nature you need. Yes.
Right. So if you go to your currency example, in the currency example, where you're talking about pesos and dollars, that could be put into the declarative format.
Yes.
And then the other operations to match and to test the inference, that could be underlying, you know, in whatever the other implementation operator is.
Yes.
That would make it a little bit easier to.
I think that's fair. Yes.
This is a more general question. So you're running this on a CPU at the moment.
Yes.
So the XOR computation would probably be similar compared to your, like for your new hardware in this. But this is a question, is it the majority and the selection operations that would be far more efficient and far more parallelizable on the new hardware, and those are where the performance gain would be? Is that a fair?
Yeah, that's absolutely fair, because like something like here doing XOR on 8,192 bits, it's translated down to like 16 512 bits XOR AVX operations, which is not that much, right? It's like, I don't know, 100 cycles or something. if you want to grab and store this. So with of course, where the real value proposition for me is in the hardware is that you don't need to load, process, and store this at all. And this is standing around so the computation can be done relatively efficiently. But like most of the cycles are actually spent moving the data around.
Yeah, absolutely. Yeah.
So yeah, so it will be useful for every operation. But you're right in your assessment that permutation and majority are the ones that are that will be really more efficient there. All right, ready for another example. So what we are doing here is we define one of those propositions. So you've seen this here, right? Cat, Tom. And now we are creating two which are inverses of each other. So inverse permutations of each other, which are subject and object. And then we are creating like a couple of symbols. And we are defining, we are applying our permutations to those symbols to get like a few statements, right? A few logic statements, if you will. So mother of mother, mother of child, etc. What we're doing then is we are defining a helper function, apply a relation, which gets a relation, a subject, and an object. And then it's gonna subject transform the relation and binds that to X. So it's saying X is the subject of this relation. So for example, Anna is the subject of being mother, right? And do the same or like analogously for Y. Then we are gonna bundle these together like we did so far. All right, and then here's the cool part. So we are gonna learn from data points again, but we are not gonna learn like a concrete model of which point should go where, but we are gonna learn an abstract model of laws, like what laws do apply here. And to do this, we are going to generate some data points that admit to our laws. This is the generate sample function. So we are taking a few people like X, Y, and Z from the general population, where this relation holds. That if X is the mother of Y and Y is the father of Z, that X is the grandmother of Z, right? And then like this is what our logic formulation looks like. And then we generate a few of those examples, which we take as data points. And we apply the same thing as we did with the circle example, namely we bundle them together. So this is our like mother rule prototype, like how these interpersonal relations characterize in general. So in average over X, Y, and Z. There are some ideas in here about how random noise cancels out, but well, what's important here is that if you do this like with just one data point, it's no better than like it doesn't work at all because it doesn't at all generalize. It just associates this rule with person X, Y, and Z. But as we saw with the factoring, right? With the factoring, like the more data points you give it, the more general this thing becomes. So here, Mary did 3 actions, and like we saw that this generalized to this. And that's exactly what we are doing here, except that the majority here becomes random data and just some noise that we can cancel out. While here the majority gave us like an object category, namely transportation. Right. So let's apply this to a specific example. Let's actually run this. Even though I've tested this before, I still like I'm a bit nervous every time I press run. Right. So the example here is with Anna, Bill, and Sid. And we are stating like a few logic statements here, namely that Anna is the mother of Bill with the apply relation function we looked at. And Bill is the father of Sid with the same helper function. And then now what we expect, what the grand truth is, right, is that our apply relation of grandmother of Anna Sid, that this holds. But we can actually compute this because we learned the rule. We learned like this implication of mother of, father of, grandmother of. So what we are going to do is we are going to shape our data like this, like the general rule, right? How things fit into this. So grandmother rule, Anna, mother of Bill, and Bill, father of Sid. And this grandmother rule should now, if everything went correctly, conceptually puts these objects as like Y and Z, and then we should get back our so it should put in these as these, which get decomposed in the different people, and then like conceptually recomposed into like the new rule. And then we can finally say that what we calculated, the proposition holding, that is like it has similarity with the actual rule. And this holds. Right. So
before you move on, do you mind showing again the definition of apply rel?
Yes. This one.
Oh, okay.
I can email you the or you can go to this afterwards and study it more and play around with it. This is in a column, so if you are on this page, you can just like copy. I realize this is in Dutch, but you can just copy the notebook and play around with it yourself, right? Okay. So we are almost done here. So we have a function here that is a generalization of the apply relation. This is applying multiple relations, which you may think about as an all formats or like a property graph or a triple store. There are many ways to think about this. We are getting some nodes, A, B, C, and some properties, PQR. They all look the same in hypervector space, so didn't bother to separate them out. We're applying this this biasing function to get new subjects and objects. So we are changing our nodes to be more like the relation we want. So you can see here the fraction, which has how much should we interpolate between like how the nodes are currently connected and how they would be connected if their only job was to represent the relation between the two nodes with the different properties. And so the only point I want to really make here is that this doesn't have to, your normal distance is not the only thing you can do in this space. You can change things in a certain direction. In this case, very importantly, our new node position and our new nodes are both, they look like random data, which is their z-score is small. They are not unusual hypervectors. Second of all, their distance is also normal. It's only like 0.4. It only has like 0.46 standard deviations less ones than you would expect. So it's absolutely normal. Distance is normal. Hypervectors are normal. Yet if we analyze the bias in a certain direction, so this takes as arguments your propositions, then you can see this is very abnormal. We are like we are almost 6 standard deviations sure that these vectors are related in a certain way. And that way is like via the relation. So this is something you absolutely need to gain a certain level of expressive power. If you cannot do this with just XOR, because like things will cancellarity or commutative, like all kinds of properties that are like way too powerful to represent like really rich data, or like it's way too well behaved to represent really rich data. This is directed. This takes arguments in how things are related. Right, and then finally we can see that if we don't apply P and Q, but if we apply R instead, that there is nothing to say about here. We are like, there is no special relationship between these. Well, we could see that there is a bias and a reverse bias that was highly significant. Right. All right. Then we are on to our final example, which is like we are coming down from a high and like getting ready for our lunch break here, which is we are just doing some logic, some like P arrow, like simple implication logic. So we take our raining and street is wet variables, and our goal is to say if it's raining, then the street is wet, and also at the moment it's raining, and therefore the street is wet. We want to conclude this. So we are going to encode there are 2 ways to do this. First way is to encode our implication as the antecedent and XOR in negative, right? So, and I think I messed it up, but it basically looks the same as you would do this in regular logic by accident, because like the head is used in regular logic to say and, right? So like the implication translates in like ands and not of the second argument, which is totally coincidence, but I will take it. Then the truth we have here is that it's raining, and the conclusion we want to get to is just binding together like the truth and the implication, and it also works with multiple implications. You will have to take my word for it. And what we can then conclude is that the conclusion is unrelated to raining. So it's not raining, but it's not unrelated to concluding that the street is wet, which is exactly what we wanted. We can do the same thing here, not with XOR, but with majority. The only difference we need to take into account with majority is like the, yeah, so this is quite algebraic. It's like quite an algebraic argument. But here in XOR, like the same thing cancels out. So if you have like A XOR A, then it's 0. But in the majority, it's actually, that's majority X, not X, Y is equal to Y, or what? Or in another way, set it in another way, that this is 0. I hope I got that right one, that last one right, but this is the important property, right? And the second thing you have to take into account if you are using majority is that you don't want to have like duplicate elements of things. So you either have to like do a weighted majority, or you have to do a threshold, or you do have to like pre-weight things. And here I'm pre-weighting things. I'm saying the truth. I'm weakening the truth of raining with like a random hypervector. So it's equally consistent as like the implication rule we have above. So all our logic rules are padded to like the same length, or like the same amount of statements in them, right? Right, that was it. Let me get back to the slides. I think I have like one more slide. yeah, which is encouraging you to go ahead and explore this. This is like a fascinating algebra, really, like, and this is not the only one. Like on the hypervector stuff, there are like multiple interesting algebras that's interrelate in certain ways. Anyways, so if you go to the HD computing, this website, yes, this website, then you can find publications, and this is like all the publications. It's kind of hard to get to, but there are also, like, if you go to the home, there are also like introductions, and one of the introductions that's really important here is the Canerva 09 paper, which shows up in my history, which like introduces like the concepts, and you will recognize some of the examples we've been to. Second of all, I want to thank Peter again for giving like a great like prerequisite like jump start to the things I've talked about. What's not on this on this website just yet, but it's likely will be next week, is the tiny library I've been working on to do efficient and hypervector computations with a lot of extra utilities to thinking about probability stuff, to thinking about the capacity, like how many dimensions do you need to represent, how many elements can I represent in a certain hypervector of this capacity. And finally, like if you go to my website, I've done like a lot of weird computing things like this. And if you want to get in touch, there's a contact and there's Twitter and what have you, right? So thanks all.
I'd also like to thank Adam for putting the work back in workshop. It was beautiful.
Yes. Thank you, Adam. You got a compliment online. Peter Tradeoff said that it was a great presentation, great workshop, and thank you, Adam.
Thank you.
Any questions from the room?
Yes, one. Okay, so for me, what would make this extraordinarily useful is to be able to have a like a language, declarative sort of language, and then so we have SQL, right? In SQL, you can create objects, you can, but it doesn't say how exactly. You can select objects and so forth, but it doesn't say how it's implemented. So it's totally, it's totally declarative, and the operations that are involved are not known.
Yes.
Right. So it seems that you have a few operations here that are very useful, but we don't necessarily need to know how it's done on the underneath.
It's partially true because like this is a very young field, and a lot of researchers actually are going to contribute. Like a lot of people that use this library of mine, like are people in the VSA world, in the hyperdimensional computing world, that will actually experiment with this. So, but there are some other considerations like scale. If you want to do this at scale, you actually want to hide the implementation because you want to mess with it, right? You want to make it more efficient. And for this purpose, there is this very recent paper called HDCC, which is kind of what you described. It's like a declarative language where you can say, like, what do you want to do? In this case, you want to do a multi-bind of a batch bind of the ID and value, which is like the records, encoding that was talked about a lot. And where you can give like hyperparameters like the number of classes, and the vector size, and things like this to declaratively do efficient computation. Yes.
Right. So, so what are the specific types of inference that you have? So the majority is one function, right? And then is there a couple of others that are the specific kinds of inference? You store information, you can relate information, yes. So, and then what is the other type?
Yeah, so I actually kind of messed with the algebra in terms of like being able to express like new concepts more easily. But if you go ahead, what does it mean to be an abstract Boolean hypervector? What you can see is that you need a random permutation. And I didn't like kind of, you also need like really efficient, be able to generate like normal hypervectors, right? And what's also, all the rest like here is implemented in other things. You need like permutation, and a specific kind of permutation that's also handy is like swapping like the two halves of the hypervector, and or like swapping like certain things. Rehashing, that this is kind of what was referred to earlier, like one of the universal encodings is hashing.
Yeah.
So that's one.
So I'm sorry to interrupt. Quick question. So do you understand? Do you know Prolog?
Yes, of course.
All right. So would it be possible to take a Prolog program, a simple Prolog program, and then as Prolog is written, and then come back with the results, like do inquiries?
Not quite. Prolog is a bit too rich, but you could do a subset of Prolog.
Okay.
Yes.
That would be useful. That would be very useful.
And so then you have the equality XOR. I also like AND, OR, and invert, even though you can implement these in like different primitives. But it's nice to also have your Boolean algebra, because it's kind of not what this talk was about. But what you can also do is you can see this as doing like mass proposition logic, where you're just doing like hyperdimensional, you're taking 8,192 truth values, right? Boolean truth values. And you're doing like a conjunction of them all, or an OR of them all, or like XOR is just actually not equal to, right? And not XOR is equal to. So you can actually have like a statements over this, and you can in fact exploit this to say, oh, I'm gonna make a network of XOR not, or of select equal, also known as if then else. So you can embed a lot of computational paradigms on top of hyperdimensional computing.
So that's the declarative language that I would like to see. You know, those in another shorthand, but not exactly.
I'm sorry, guys. I don't mean to interrupt, but we also got to get to lunch, and Ben is going to give a few words. So can we just take these questions offline? They're great questions. I'm also interested in the same thread. So I saw you had a question, but if it's okay, if we could just.
We've got as Edward just pointed out, we've got a little bit of a schedule revision. So
we got a hard stop today.
Yeah, we do. We'll have Ben present now in this workshop. Then we'll let this workshop close for the day. We'll take other questions offline, and we'll host Anton Colden's afternoon session up here where it's a little bit more comfortable. So we'll bring everybody up here. That's the only afternoon session going. And so lunch folks may need to miss something with their sandwiches over here that we can grab after Ben's talk that would be relatively quicker. But Anton will start at 1:30. It's 12:30 now, and we'll hear a bit from Ben.
Thanks everyone for the questions. Let's
I should go into Zoom tonight.
Go into Zoom.
Where's the link?
I think I'm sorry.
Channel and stuff.
DM. Yeah.
Okay. Also, like questions, not just proof. It's folder, something like that.
Yeah, Ben Gertzel needs no introduction, so we'll hop right into it.
Yeah, and I'm gonna talk for just, do we need a mic?
No?
I'm gonna talk for just a couple minutes since we're so close to lunch, and what I have to talk about, unless one gets into engineering details, is pretty simple anyway. And the crux of it is an idea I've been thinking about for a number of years. I mean, the high level motivation was introduced by Rachel in the start of this workshop, which is, I mean, we've gone a long way in deep learning, for example, by optimizing hardware better and better for the sorts of neural learning and inference algorithms that we have there. It started out with using GPUs tuned for graphics, and then you have all these architectures tuned for neural stuff. So when you're looking at other AI architectures and algorithms, such as OpenCog Hyperon, for example, or hypervectors, as we've just heard, I mean, then you have the question whether some custom form of hardware can accelerate that in the same way. And the key operation that you need to optimize to make OpenCog based AI fast is pattern matching on metagraphs. And this is characteristic of most software systems that are engaged with manipulating large graphs. I mean, almost all the workload there is reading and writing to the graph rather than doing number crunching or something. Whereas in computer graphics or in deep neural net applications, most of the work is in multiplying matrices to update the weights on a network. It's different. In graph-based systems, you got this big graph in RAM. You usually like doing a pattern match of some sort across the graph, grabbing some bits and pieces of graph out, combining them together, and then putting some more stuff back in the graph. And putting it back in the graph is not usually that expensive if you know where to put it, right? But finding this stuff in the graph is expensive. So I mean, we have the whole OpenCog Hyperon architecture, which I talked about a bit in the workshop 3 days ago. I mean, you have atom space containing nodes and links. You have a distributed atom space. You can have a neural space. You have the meta language, which can compile into Rolang. You can have large language models connected. But in the end, whether through meta directly or through meta compiled to Rolang, as well as looking at distributed stuff, he's doing a lot of pattern matches against atom space based in RAM, right? And I mean, Rolang optimizes this in some ways. By compiling meta to Rolang, you can make better use of hyperthreading and so forth. But of course, there's only so many hyperthreads, right? So I mean, if you had a chip design that's specialized for metagraph pattern matching, then of course life becomes much easier and things can go much faster. Now, I looked at GraphCore and some other graph processing chips, and unsurprisingly, it comes out hardware is very specialized. So, I mean, GraphCore, when you look at it, is very optimized for things like graph convolutional networks, where you're mostly concerned with iteratively updating floating point weights on lengths of a graph or weights associated with nodes of a graph. And if you're mostly updating discrete stuff associated with nodes and links in the graph, then a lot of the floating point firepower on a graph core is wasted, and you, by the same token, you're not using that part of the chip for what you really need. Now there are discrete operations. I mean, there are floating point operations, of course, in OpenCog, so it's not totally wasted. It depends what you're doing, but an awful lot of what we're doing is more discrete. And given this is a fairly heterogeneous architecture, there's a lot of aspects. So if you have a neural space, like a neural atom space, you might want a graph core for that. You might want a traditional deep learning chip, right? And you can also take nodes and links in atom space and embed them. I mean, we've embedded them previously into, say, 50-dimensional vectors. You could also embed them into hypervectors, right? So you can embed each node or link in the atom space into a hypervector. Then certain sorts of searches and manipulations will be done very well on these hypervector embeddings. And for that, that the Simuli hypervector chip is one option. And I mean, there's other specialized chip architectures out there that are also probably good for these hypervector operations. But before I had met Rachel and found out what she's doing, I started to think about what could you do in terms of a specialized chip architecture for metagraph pattern matching. And I don't know too much about hardware. I have a bunch of friends who know more about hardware. So pretty much I started going through the literature to see what specialized chips there were for graph processing in various ways. Started to think about how would you kind of hack that to deal with metagraph pattern matching, then bounce the ideas off a few people from the hardware space. So among the various papers I was looking at, there's architectures like this, and there are many architectures like this. This paper is one example, which is better in some ways and worse in others. But this is processing and memory architecture for processing large graphs. And pretty much what they do here, they take these processor cubes, which you can just buy, and each processor cube has like eight layers of memory, and it has some processor and a controller associated with it. And what they do here, they lay out these cubes in a square grid, and pretty much they take the graph and partition it. So they're dealing with the case where the graph doesn't change too much, right? They take the graph and partition it among the squares in this grid, right? And I mean that leads to very obvious implementations of many graph algorithms, right? So you're searching for something in a graph, well, just search separately in the part of the graph in each grid, and then collate the results together. Now it's not quite as simple as that. I mean, you'll have links between a node in one cell and a node in another cell, which you have to deal with. And periodically, which is a quite expensive operation, you want to be able to move stuff from one cell to the other cell. But as the hardware works, pretty much you have to freeze processing in order to move stuff between one cell in the grid to another. So you're not able to reorganize the graph among the grid cells in real time. But so they give nice results from simulations of this. I'm not sure they ever actually built this particular chip. There's a bunch of other architectures out there, but when you dig into it, similar things with some changes can be done for metagraph pattern matching. So Rachel and I worked out some of these particulars together and bounced them off various people from the hardware space. No one found any obvious problems with sort of adapting these graph chip designs to metagraph pattern matching. Pattern matching is a different algorithm than the ones that they were considering. But the basic architecture is then you have these hybrid memory cubes, which have processor and memory in them. I mean, inside each cube, you have a bunch of different little memory vaults, and then you have some additional RAM. The vaults each have logic units and a local memory cache. So there's some parallelism within each cube. But the nice thing is you can just buy these cubes from a supplier, right? So then, creating this overall chip from these cubes, there's still care. It's still a thing to do. But the hard part is really in building those cubes, which manufacturers are already doing, right? Then you have a global RAM that all the cubes have access to, where obviously the access there is slower than to the memory cache inside each cube that you have. And so then the logic units, which are inside each vault, right? The logic units, you're dealing with both discrete and floating point processing units there. And at this level is where things start to operate differently than a graph core, because the graph core is just focusing on floating point operations when you get down to this level. Whereas we do want floating point, but we need fast discrete processing at this level, and you can tune the particulars of the discrete processing unit based on what you need to do pattern matching effectively on the graph, which gets more and more detailed. Now the memory cache also is interesting because you have the opportunity to put sort of ECAN or Hopfield net type activation spreading stuff like at the hardware level. So there are many interesting parallels between this and the distributed atom space, actually, because with the distributed atom space, you have a bunch of different machines that have parts of the atom space memory graph, right? And then moving atoms from one machine to another is much more expensive than rearranging them within RAM of some machine. You also have a persistent store, and then you need to do some clever caching to figure out what comes out of the persistent store and stays in RAM for a while, right? So here you have a similar set of issues. You want to determine what stays in the memory cache, which is in a given vault, which is inside a given cube. Now, the difference, of course, is here, you don't have as much memory to work with because everything's being put on the hardware. On the other hand, activation spreading type heuristics are not very expensive, right? So putting activation spreading sort of heuristics for determining what should be in the cache here is an interesting infusion of some simple but potentially powerful AI down to the hardware level in a way that's different than what is done in the graph chip that I mentioned. Because if you're just doing sort of standard graph algorithms, doing activation spreading for your memory cache is not necessarily going to do what you want, right? Whereas if you're doing this sort of semantic pattern matching on an atom space representing the mind of an AI system, often using activation spreading of various sorts for your cache is what you want. So here, with stuff like the cache management policy is one place that you're like fine-tuning the chip, not just for pattern matching, but for this sorts of pattern matching that you wind up doing in building a cognitive system. So, for example, if you were trying to use this as a backend for a Haskell compiler or something, the sorts of optimization you do for the pattern matching inside Haskell are not necessarily the same as the sorts of optimization you do for the pattern matching inside a cognitive system, because the cache management policy would not be the same. So you have, you have an overall pipeline then going from the OpenCog Hyperon software application finally down to these memory cubes, and the double mesh I'll explain in a moment. You need a special compiler that takes the pattern matching in the atom space and compiles it into something that will run on the hardware. And you need something to partition the graph in the right way. And if you have a graph which is always changing because you're doing like hardcore code self-modification or something, then you just don't put it on hardware, right? The case ideal for this is like you've parsed all the knowledge in Wikipedia or something, or you've crunched a bunch of data sets, or you've just learned some body of procedures for dealing with a certain class of situations, which you know is really good for dealing with those situations, right? Then it's not that you can never change that, but changing those nodes and links is not the main thing you're doing. You're more often just using it to do something. So if that's the case, put it down on hardware, then you can do pattern matching on it quite efficiently. So it's a little bit like the distinction between model learning and model inference in the neural net world, but it's not quite as rigid. And one thing we figured out after a while is that moving nodes from one cube to another is a quite costly operation, and you actually have to freeze everything happening to update the memory everywhere in an effective way. So what I think you end up doing is, if you always want things to be operational, like you take your current memory grid, copy it to a second memory grid, then freeze that guy and reroute everything on that guy. And then when you're not doing any rerouting, you just have two copies, which is, if you're accessing the thing a lot, is fine. You can rapidly access the two copies. If you need to reroute things because the graph changed, so it's no longer optimal to have the nodes grouped together that were grouped together, then you just freeze one of the grids and reroute on there, but you still have access to the other one. And I mean, it's all not easy. I mean, there's a lot of programming to do, but still you're sort of putting the Lego blocks of these cubes together. So it's not incredibly hard compared to many things in chip design. Yeah, Adam.
Yeah, why do you have to copy it instead of being able to route the traffic to one mesh or another mesh?
Well, if you have updated one mesh because it's better, why do you want to leave the other one old though?
No, like I mean, you're routing it to one that has already updated while you're updating this one.
Well, that's true, but then you don't want to redo all the work to update the other one.
Oh, right.
Just copy the updated version over.
So it's easier to copy than to update.
Yeah. I mean, because the hard parts. I mean, the hard part is just sending stuff between the cubes. It's not any harder to send stuff here than to send stuff between the cubes, and then you're saving just the computational operations done. So, I mean, we've designed this, and we've got to go the same route as with the other hardware that's discussed. I mean, we've got to go to FPGA, and then once you have it running on FPGA, there's many shops in Shenzhen and elsewhere that will deal with the next step for you. But going to, probably we will do a step before that, and I'm talking to people who are good at doing simulations of hardware. So then we'll probably do sort of a software simulation just to tune all the parameters of everything, because there's nice chip simulation toolkits in Rust, and the atom space for Hyperon itself is in Rust. So I think we can make a nice software simulation of all this and connect it to the actual Hyperon pattern matcher. Then that will let us tune all the quantitative parameters of everything and the specific logic operations before feeding it to an FPGA guy. So we bounce this across a couple experienced hardware engineers who seemed happy with it. But exactly how much speed up you'll get, I mean, we just sort of have to run simulations to tell, but it will also depend on sort of the size of the patterns and the nature of the atom space. So trying to do sort of rough back of the envelope calculations, it seemed to me that if you had, say, Wikipedia parsed into logic, right? And then you're doing pattern matches of the sort that you have for natural language query processing, which is only one sort of thing to do. But it seems that then a vast majority of the time, you're doing like a small lookup, which is going to be within the part of the graph stored in one cube. And Of course, you can do fancy things like nodes that are at the edge between the two. You can just store copies of them in both. So if you have small patterns, there's very small odds that they're gonna span between the two of them. So if you're dealing with that sort of case where it's a pretty static graph, like the knowledge in Wikipedia, and it's a small pattern like you get from a typical natural language query, then pretty much the speed up should just be proportional to the number of cubes in the lattice, because you're just searching everywhere in parallel and then taking the best answer you got and delivering it, right? And then other cases where the graph is a little bit dynamic or the patterns are bigger, depends more heavily on the particular statistics of the graph, right? So I think what Rachel and I have been scheming is then like an AGI board where you have deep neural net chip, hypervector chip, OpenCog pattern matching chip, CPU, and you're wiring these together with sort of fast processor to processor interconnect and have some shared memory among all these things. And it seems like, hypothetically, if all goes well, a chip like this can do for Hyperon type AGI something similar to what GPUs did for matrix multiplication based AI. Now we don't have what they had, which is computer graphics as a huge economic driving factor to link toward those chips, right? I mean, but we're building something specifically for our AI system. But I would say there's a lot of other applications out there where you have large graphs and want to pattern match again. So I mean, every social network has that problem. I mean, the intelligence agencies, while not my favorite customers in every respect, I mean, they have that problem also, right? So while the motivating factor here is Hyperon, I think there would be many other applications where pattern matching against a large, slowly changing graph needs to be sped up, right? I mean, and Cray has graph processing supercomputers also, so there's various approaches out there, but it seems like doing this sort of MIMD parallel processor in RAM tuned for pattern matching has not been done before on graphs, let alone metagraphs. And that's it, relatively short and sweet.
That's great. Thank you very much, Ben. Any questions from the room?
Got some questions.
One question for the graphs. Were you considering storing them as triples or storing them as vectors in the hyperdimensional representation?
The hyperdimensional representation.
In the vector representation, were you going to be using them as
Separate things. So I think I think maybe
you're asking about hypervector embeddings?
Yeah.
I mean, so first of all, this particular chip design is not based on hypervector embeddings. I mean, you could explore that, but that would be a direction we haven't gone, right? Because if you're making a hyper embedding of the nodes and links in the graph, in the chip architecture in the board architecture we're looking at, the most natural thing would be to then do the work on those hypervectors in Rachel's hypervector chip or some other variant there. I mean, hypothetically, you could try to take the hypervector chip and the pattern matching chip and like make a version of the hypervector chip that's layered on top of the pattern matching chip. But we haven't looked at that yet, and I'm not sure if it makes sense. So in this chip design that I just outlined, you're not using a hypervector representation within each memory cube. You're using some other efficient graph representation. Adam wants to say something.
Yeah. So two intertwined questions. One question is, you know that like many natural graphs follow this Zipf distribution, right? This power law distribution. And when I look at the chip, yeah, I see like squares and like maybe at most cubes. And to me, there is like a topology mismatch where you want to break up like large nodes like you have a few very large nodes, and they need to be somehow distributed over this mesh. And then the intertwined question is that in a graph, distance is really weird, right? And it's very hard to project it into 2D or even like 2D times 3D.
Well, so you can make multiple copies of the same node. So if you're doing natural language or something like it, I mean, a node representing a function word like of or something. So you could have a copy of that node in multiple squares, and in that way, this is very similar to distributed atom space, right? Because you will want to do the same thing in distributed atom space. So if you're looking at like Zipf's law with natural language, there's not. I mean, precisely because of that law, there's not that many nodes that you would need to copy and put among all the different cubes, and everything in the long tail you don't have to copy.
So you're flattening the distribution a bit by
a bit, but
yeah.
But even it's going to be more like 1/10 of the nodes in each cube are replicated. It's not going to be like 80% or something.
And then the intertwined question, just to repeat, was like, how do you deal with the locality? Is it also by the copying? Like, is that like the same solution for both questions?
Yeah, it is. Right. Yeah. At least I can't think of a better solution at the moment. Yeah. And the elegant thing there is that all these things occur in a distributed atom space also, right? So, yes. I mean, with this design, because it's all sort of partitioning based, and you're dealing with the idea that processing within one partition is much cheaper than going between them, and rerouting is costly. So that the nature of the constraints is kind of the same on distributed atom space level as in this sort of MEMD parallel thing. And then the quantitative parameters are all going to be different. So you need some tuning, but the conceptual approach is kind of similar, which is elegant.
The thing I did not fully understand is the expressiveness of the possible or the set of possible rewirings. So, because you showed two graphs, one where we had just cubes, like on a matrix of cube, and one where cubes were layered, and so I don't understand which one is the physical one, which one is the abstract one is, and
everything shown there was physical.
Okay.
Or was a pictorial depiction of things that are supposed to be physical once we build them. But it's also all physical because we're in
so
the
what are the constraints? What are the constraints in terms of wiring a cube to another cube?
I don't know to be honest. I mean it's the same as in the paper I referenced and others, but I mean of course the quantitative, I mean the speed of transmitting stuff between one cube and another is it's much slower than propagating stuff within a single cube. Right, but I don't actually remember the exact proportion.
I mean, you have a cube here, you have a cube there. You're not going to be able to connect them directly. Right?
That doesn't make such a big difference. I mean, but cube to cube is much more expensive than within a cube. Yeah.
Right. Yeah. This is clear. Okay, because you were talking about, okay, we're going to copy from different meshes so that we can rewire, reconfigure, and I'll tell you what that means.
Well, to rearrange, the point is that you've partitioned a graph, right? And the obviously an atom space graph isn't a partitioned graph, right? So you're partitioning the graph in some approximate way among these different cells, right. And to count for things that logically should live in more than one partition cell, then you're making copies of some of the nodes, putting them in multiple graphs. Yeah. But if you have a lot of reasoning going on, then the graph itself is changing in topology, right? So then at a certain point, after the graph has changed in topology enough,
Yeah.
then you're going to want to repartition, right? And the point is repartitioning the graph is expensive operation.
But isn't that, in that context, isn't that when you're not changing the physical connections between the cubes, isn't that just
No, but you're
copying
changing
stuff around?
what goes in the memory of each cube. No? And
Right.
you're just like potentially refreshing the whole memory of each cube.
Yeah,
right?
and so that's the
Yes.
operation that requires pausing.
Yeah. That's right. Yeah.
Any other questions before we pause for lunch? So Anton's session starts in 20-ish minutes. We'll be up here, like I said. Welcome to pop out, get your lunch. That session will start with Patrick Hammer and Peter Isev, I believe, doing a presentation, and then Anton second. There are sandwiches at the break area, so you're welcome to just grab a sandwich and stick around. And then in the box back in the back of the room on this table back here are the conference proceedings. So
is it any different from the PDF that you can download?
I don't believe it is. So, yeah, but you can have a physical memento.
This one is a physical object.
Yes, it is different.
It's not merely a simulation.
Yeah, we're taking that.
If you catch it on fire, if you let it on fire, it doesn't smell as bad.
In the very back on that table is a cardboard box.
So the hypervectors presented, it seems like, wow, this is amazing, and so on. But then you realize that, with that size vector, beginning, you probably can't have more than 1,000 categories of them. And then suddenly, okay, well, that's not